So, thank you so much for joining this workshop in the frame for EO4GEO project. This workshop is organized by the Laboratory of Atmospheric Physics, University of Patras, and is dedicated to air quality monitoring and management. It is supposed to be constructed and followed by advanced users, so people that know at least the basic about air quality, and you will see then the learning outcomes, what is the scope of the workshop, etc. It's 4.5 hours workshop actually. At least there is a coffee break between. It's in the frame of it belongs to the overall role of EO4GEO project, which is about to to learn new scientists about how to use data coming from Copernicus, either from in situ satellite measurements or models. So this webinar aims to provide advanced knowledge for air quality and management. You see that you will be informed about there are three axes, actually the use of Earth observation technologies and the data in different time and temporal scales, as well forecast about air pollution, and how to use what type of satellite data or ground data are available, and how you can use them in air quality planning and decision making. And what is the relationship among the emission sources, the meteorology, the dispersion of air pollutants, and how we can use this in practical applications. So there is an agenda. I will not give you the full program. You have all your program with some kind of information material. You can follow the full program from there, but it's also important for us to go on the back page and sign your agreement about the recording. It's obligatory. So at the end, we need to get to receive all these requests back. So the agenda has 4 sessions. The first session is about the basics of air quality for monitoring and management. We'll see, it will be 3 or 4 talks on this session. Then we'll go to the ground truth. So we're going to in situ measurements in the urban environment. What type of measurements do we have? How we can build a network? What are the outcomes? Then we go from pollution from the sky. So we get the Earth observations from satellites, and we'll see how this can be transformed to insightful information for air quality in an urban area. And the last session is about air pollution modeling, what it is, what they can tell us, what are the advantages and disadvantages. Just a few words about the lab. The Laboratory of Atmospheric Physics has been established quite many years ago. You see some of the basic research axes about environmental time series, homogenization, and climate change information, about stable isotopes in the atmosphere, about ultraviolet radiation, taking account measurements, effects to humans, etc. Solar radiation measurements, forecast, research and assessment in general, artificial intelligence in the bucket of environmental data, and weather and atmospheric pollution forecasting. And this is the EO4GEO. The EO4GEO, you see that it has a quite long title. It's about towards an innovative strategy for skill development and capacity building in the space geoinformation sector, supporting Copernicus users update. So it's a big project, too many partners for at least 4 years now, and we have 6 months more, yeah. And the idea is that there is a lot of information around, coming from the Earth observation sector and also from the GI sector, geographical information. You know, you are familiar with GIS. And we need new scientists to use this information effectively. The amount of data is huge, and you need to have the right skills in terms of technical skills first. So EO4GEO tries to go to the EO-GI sector, receives what is needed for new scientists in terms of technical skills, and try to provide training material for the newcomers. So there are predefined curricula how to build a lecture, a course on about this subject. Training modules, if you will follow the EO4GEO webpage, you will see a lot of training material. Maybe some of you have already participated in some of our previous webinars in the frame of this project. There is a lot, much more webinars in the EO4GEO webpage. There is a mobility program, something like the Erasmus Plus for practice, for internships in the private sector or in other institutes, and a long-term action plan at the end. So, I hope you will enjoy the workshop.
I'm very happy, I think, and I'm very happy to guess that you have happy faces behind your masks. So, I'm Vasilis Salamalikis. I'm working with Professor Andreas Karatsidis in the Laboratory of Atmospheric Physics at University of Patras. And in this presentation refers to air quality basics and some introductory aspects about the Copernicus program. So starting from the initials, some definitions. Air pollution is the atmospheric condition where the substances are present in concentrations that are a concern or even an immediate danger for human health, ecosystems, infrastructure. So these substances are called air pollutants, and air pollution, together with air pollutants, are combined to define air quality, which refers to the degree to which the air is suitable for humans and the environment. In general, a human can survive with a polluted air for 3 minutes. Thus, breathable air is the first requirement for surviving. In terms of air quality, survival time differs depending on the type and the concentration of the air pollutant, and also the exposure of the receptor. The receptor is humans, ecosystem, microbes, animals, and infrastructure. This slide shows how can we illustrate the cycle of air pollution. So the cycle can be divided into 4 parts. The first part is the emissions. The emissions could be man-made, and specifically agricultural activities, energy production, waste, coal mining, transportation, etc., and also natural sources, including emissions from volcanoes, dust storms, and sea spray. Then all these pollutants can format other pollutants via chemical transformations and the interaction with sunlight. And then this soup of air pollutants can be dispersed due to weather. And finally, we have the impact to the receptors. In this slide, we can see the time scales of the basic air pollutants. The time scales, the spatial temporal scale we can categorize 3 distinct regions in this graph. The lower part describes the short-lived radicals. They have short temporal scale, short residence time, and also a small spatial scale. But the most important for us is the urban and regional air pollutants. The spatial scale can range from 1 kilometer to thousands of kilometers, and also the residence time can range from hours to years. From these air pollutants, we can describe the basic air pollutants, including the carbon monoxide. The carbon monoxide is an odorless pollutant coming from combustion, and the climate impact is that contributes to the formation of ozone, and also it can be oxidized to give carbon dioxide. And then the NOxes, the nitrogen oxides, the primary emission sources are fuel combustion and soils. And climate impacts, they contribute to eutrophication and fertilization, and also they act to produce ozone, the tropospheric ozone. Then we will move to sulfur dioxide. The emission sources are both natural and man-made. The natural includes volcanoes, but the man-made include combustion and industrial processing. They form the acid rain and also the air particulates. The tropospheric ozone, it is a secondary air pollutant. It is formed from VOx and NOxes, from volatile organic compounds and the nitrogen oxides. And the basic climate impact is that it changes the radiative budget in the atmosphere. Now in this graph we can see also the particulate matter. Air particulates have different sizes, different composition, and coming from several sources. The climate impacts include the changes in the radiative transfer in the atmosphere, and also the reduction of visibility and the variation of albedo when accumulated to snow or other surfaces. We can see here the size of the particles. We have the coarse particles that we have particles with diameter less than 10 micrometers, and fine particles with diameter less than 2.5 micrometers. And here we can compare it with human hair. The life cycle of particulate matter is illustrated in this graph. So we have many emissions, and we have a soup of chemical reactions. So from the nucleation mode, we can go to the coagulation mode, etc. And then we have these deposition processes, including the wet deposition and also the dry deposition. But can we combine all these pollutants, and what are the impacts in health? Different air pollutants have different impacts in health, but the most important thing is that in this graph we have the pollutum of air pollution. It combines the population affected by air pollutants and the adversity of effects, and we can see that as the adversity of effect increases, we have more deaths. Okay. Now, okay, we have some implications about air pollutants. We care about some air pollutants, but what about the measurements? We have two directions for retrieving measurements. The first direction is to buy an instrument and go to in situ measurements, but in this case we are limited regarding the spatial scale, but we have high temporal resolution. The alternate is to use satellites. Copernicus program do it for us. Copernicus is the European Earth Observation Program looking at our planet and its environment to benefit all European citizens. It provides information for several meteorological, climate, and air quality parameters. And the basic is that it's free and openly accessible to users. So with Copernicus, we can monitor climate, marine monitoring, atmosphere monitoring, etc. Moving now to this strange graph, how can we use Copernicus to retrieve our data? It's very simple, because we have to go to this website, and we have to register or to create an account. Then we can log in, and we have the first page of this graph. This is the first page after our login, and we can scroll to all these windows, and we can search deeply the website. But if we are interested only on data, we can move to data sets, and we have plenty of options here. In this case, for this example and for this webinar, I choose the CAMS European Air Quality Reanalysis. After that, these CAMS reanalysis products provide us forecasted values and reanalysis values analysis values for numerous pollutants. Here we can choose all these pollutants, but my selection was limited to the carbon monoxide, the NOxes, the particulate matter, and also ozone. We can choose every model we want. The altitude level, the level above the altitude above the sea level surface, and also the starting and the ending date. I choose forecast for this example. The forecast will start at 0, and then we have 96 hours forecast values. After that, and after the selection of the area, even we can choose all the world, then we will submit this request to Copernicus, and Copernicus will provide us the data. The other thing that we can do is to see this API request, and then we can download this API request using Python or other programming languages. After that, we can see those maps. We can download the data and make some maps, or we can extract our data to a specific location to draw time series, etc. So in this graph, we can see the spatiotemporal patterns of carbon monoxide and sulfur dioxide. Guessing now that the primary source for the carbon monoxide is combustion, we can see that in megacities and in other cities we have values in this green region. Now for sulfur dioxide, the things are worse here because we have the industrial processing. And now moving to NOxes, we can compare these two maps. In this map, we can see the nitrogen monoxide. We know that the nitrogen monoxide and the nitrogen dioxide contribute to formate ozone, and as we are moving within the day, we have increasing concentration in the nitrogen oxide. Using both this information, we can extract the tropospheric ozone. So if we compare these two maps from the Copernicus data, we can see that increasing concentration, we have increasing concentration in megacities, etc. Another thing is that Copernicus provides us PM data. So we have two examples here. We can see this time scale increasing from before 2 days up to today, I think. And we have these concentrations in the Greece mainland with higher concentration in the megacities and here in Thessaly, etc. But also we have another source of information in these maps. You can see that as the time increases, we can measure the dispersion from 1 hour to another hour, so we can check in a specific location what is dispersed using this kind of information. To conclude with this, we have several options with Copernicus, and we can download all data to retrieve all forecasts and also analysis data. So it's time to close my presentation. Thank you very much. And I think I'm on time, okay?
Well on time, actually. Anyway, this presentation is about air quality monitoring and management. It's not a very technical one, but it's supposed to give you, the full view about what would be needed if you're going to be air pollution consultant or an atmospheric scientist in the future, and what are the challenges that you have to face. So why do we need air quality monitoring and management? The first is that you cannot manage what you don't measure. So if you're going to manage air quality in a city, you have to have measurements. You have to know which type of pollutants are crucial and how leveled are their concentrations, as well as many other metadata that you need. So, and afterwards, you will be able to manage air pollution. You cannot manage air pollution blindly just by saying, okay, I will reduce car traffic. Of course, the reduction of car traffic is it's valuable. However, it may not give you the feedback that you want, you're supposed to have in your air quality levels. Maybe you have another source like the industry, which is much more important, so you have to focus on industry and take measures there instead of just taking measures in for different sources. So, the core for air quality management is always science, and the science has a practical phase, which is the monitoring system, the models, the data handling, the evaluation of the results, the reporting, etc. And then, from sciences, you have the outcomes. And the outcomes is the strategies, is the policies, is all the decision making that we need to have. First, if we want to talk about air quality in an urban area, we have to define what are the critical values. What is important? When do we have poor air pollution, good air conditions, etc. So, this is the European Air Quality Index. It's a very useful index in terms that it has some values for the basic pollutants like the PM2.5, PM10, nitrogen dioxide, ozone, and sulfur dioxide. But most importantly, it is a color index. So this is an index that is given to the public, and even from the color, the citizen can understand if the air quality is good, fair, moderate, poor, or very poor. So all our actions to measure and monitor and make decision-making, go for decision-making for air pollution has to be based on this index. We have to change to reduce the air pollutants that are critical in our urban area in order to go from red to light blue, if possible. And if you want to plan the air quality in our city, we have to take into account there are two critical factors here. First is the emission inventory, and then it's the monitoring network. And then we have to make a plan, to have a matrix about the actions that we have to follow. So first, to adapt the air quality standards. This is the European Air Quality Index that I was telling you about. First, have a monitoring network, because you cannot manage something if you cannot measure it. Then, develop the emissions inventory. This means that you need to know the sources in your city. Which are the basic sources? Is it traffic? Is it industry? Is it harbor? Is the airport? What it is? Then you have to develop the control strategies. So you have to find ways, strategies how to reduce the air pollution when you have critical levels. You have to test the strategies. You have to use models at the beginning. So in theory, if I do this, if I will change I will make a pedestrian way the Mezonos Street, what will be the effect on air quality? You have to use a model in order to test it. Then, of course, if the result is good and the air pollution level will be reduced, then you have to do it. But if you want to do it, you have to involve and educate public on strategies. So you have to try to convince the politicians as well as the people that this is useful, because otherwise you will not get any attention from them, and this will not happen. And after the acceptance of your plan, then you can go for the development of the plan and the adoption until the end. So it's not just science; it's a whole strategy that you have to follow in order to have an air pollution plan that will work. for sure. So I don't know if you are familiar about what is the emission inventory. The emission inventory, as you see here, is a complete list of all sources and all pollutant emissions that you have in your area. So you have a specific geographical area, not only the city center, also the surroundings. You cannot find the regional sources like Sahara dust outbreaks, but you have to include the nearby harbors, the industry, the agricultural activities for biomass burning. Now that you have the crops of the olive, for the olive trees, and you have, it also covers a specific period of time, and time is crucial. So this is the emission inventory from now. For now, in 5 years, the emission inventory would be different because traffic changes. It also has some seasonal dependence. It's not the same sources all the year. Okay, let's say if you have biomass burning for domestic heating, you have huge sources during winter time, but you don't have it during summertime. So time is also important. And what the emission inventory can tell you where air pollution is emitted, very important, how much is emitted from each source, and what sources are most effective to control. So you have to go to the big sources, at least at the beginning, and try to make plans and take measures from there. However, the emission inventory cannot tell you everything. So you have all these sources, but the emission inventory cannot tell you the distance that the air pollutant emissions are transported. So they don't give you the dispersion of air pollution into the city. You don't know it doesn't give you quantitative information about the air quality level. You don't know how the citizens how much they are exposed to the air pollution, and of course you don't know also the health risks that comes from air pollution. So, however, is needed, and it's needed for these reasons. You have to identify the source and the critical pollutants. We have to identify how they are distributed and how they are changing throughout the years or during the years. You have to use it as input in air pollution monitoring. I mean, it's very important to know the sources in order to put the stations. Okay? And also, it's very important as an input for the air quality modeling, because the air quality modeling is it's a chemical model that has some emission sources, and it has also the meteorology for the dispersion. So you need to have the right input. And of course, if you know the inputs, then you can go to the strategies. So how can you build an emission inventory? You need these 4 basic sources: the point sources, the area sources, the non-road mobile sources, and the on-road mobile sources. Okay? This is the basic. I suppose that from the pictures you can easily understand what the point sources are. So you need all of them to put them in your emission inventory and have, let's say, a data set that represents which of all these activities and how much they contribute to air quality. And then we're going to air quality measurements, and then maybe we have to define what is air quality. Air quality is not just air pollution. I mean, we have a pollutant, nitrogen dioxide. Okay, you can measure nitrogen dioxide everywhere. It's supposed to be a pollutant, but air quality is highly related to the index that I was showing you at the beginning. So you may have nitrogen dioxide, but how important, how unhealthy the atmosphere becomes if you have this concentration of nitrogen dioxide. This is important for air quality. So we may have nitrogen dioxide, but the atmosphere could be considered as clean. Okay? Then air quality is the reason, as you can read it here, for air pollution control programs to protect public health. And then you have to take into account that there are short-term and long-term effects of air pollution. So it's not just a matter of an event with very high particulate matter that will take place for 3, 4, 5 days. and this will have an effect on some people that have a problem with, with lungs, with all this type of people that they face health problems that are highly related to the air that we breathe. But also it has chronic effects. So the long exposure, even to lower air pollutants concentration, may give you some chronic health effects after some years or decade. And what we measure, we have three classes of measurements. We have the measurements of emissions, which is called source sampling. So you go to the emission area and to get measurements from there in order to know how much pollution is emitted. We have the meteorology, which is very, very important for the dispersion. And we have also the ambient air quality. Ambient air quality is just a normal station at the, at the city center of Patras, measuring what are the air pollution levels at the time. But this cannot give you directly the emissions, and is highly related to the meteorology, how the air is dispersed, how air moves from the source to the measurement that we have at the city center. So then you have your city, and you want to be the air pollutant consultant, and you have to select the measuring sites. Okay, there are some general requirements. Let's say what you want to monitor, how many instruments you will have, to have safety and security in the place that you will put the station, to have access, to have Wi-Fi networks in order to get the data in real time, etc. This is the general purposes. Also, how much time you want to measure. Is it going to be a permanent station, or is it going to be just a station for this winter? Accessibility. Then you need meteorological stations as well, because you need to know the meteorology. You need to know the meteorology in the urban area, not just a meteorological station at the airport, which is about 20 kilometers away. And then you have to choose the right equipment, follow the calibration procedures, and do all the handling of data that you have for all these stations. So you have the monitoring, and the monitoring is needed for some very, very specific regions. So the monitoring gives you the possibility to establish the monitoring network, to determine the key pollutants, not just what is emitted, but what type of pollutants are in critical values, so you have to reduce them. To establish the guidelines and measure these concentrations and go to the strategies. Then you have the modeling. The modeling has been described before. You test the control strategies there. You say, okay, let's do this. Oh, and you cannot do it in practice. You say, okay, if I'm going to do this, what will happen? So you need a model for that. The model is always validated against the monitored air quality data, and you can have the evidence. You can have small corrections. You can make changes in strategies after the application of the strategy. So you apply the strategy, you apply your solution, and then you can see if some small changes, what will be the effect when you have some small changes in your strategy. So just some sensitivity study of the strategy when it's applied. So now you're going to the control strategies, and you have to determine the key pollutants, review the contribution of pollution from source sectors using the emission inventory, and evaluate the control strategies, which is the most important. Then, if you have a control strategy, you have to ensure legal authority to enforce these regulations. So you have the authority to do it. This is very, very important. If you are a university, you don't have an authority to do something for the air quality of the city. There are other agencies that are responsible. And then outreach all the stakeholders, the industry, the general public, etc., for compliance. Okay, what are the lessons that have been learned if you, from previous efforts, if you want to follow all the steps? You need a reliable database, for sure, for air quality. You need a lot of documentation, reporting. You need a lot of computer science. You need a lot of training, how can I say training, throughout your career. There are new models, there are new measurement techniques, there are new instruments, so you have to do a lot of training. There are control strategies that can vary depending on the sources, on the feasibility and the acceptability. Feasibility is another important factor. You cannot say, okay, I will close the harbor because the harbor is a very important pollution source in the city. It's not feasible to close the harbor or to close an airport or to close a main road in the city. It has to be feasible, and of course it has to be acceptable. And you have to take into consideration that the public should be, take place and be aware that there is a problem, so you can have all the acceptance from the public, and then you have the acceptance also from the policymakers. So, this is more or less an air quality management system. You have the basic, which is actually the air pollution. We have the emission inventory. We have the measurement. We have all the data for mapping, the GIS, etc. You have all the background data like the land use and etc. You have the models, and then all these are in the database, and you give the outcome. And then the outcome is represented somehow. It's given to the users, and now you have a full system here that you can play with that, and you can go to make plans, to make strategies, to make decision making. So we'll talk about today the measurements. We'll talk about how we can define the basic emissions sources from the measurements. We will talk about the models for sure. We will talk about satellite information. And then you have a full view of all the pieces of the puzzle. And it's up to you to be an air quality consultant in the future. This is my talk, actually. I don't know how much time I
have a question.
You have a question? Okay. Wait. Is there a question from... Yes, please.
Before you say that we have three types of measurements. You say meteorological and ambient.
Yeah.
What's the difference between them? Because you said that ambient air quality, it's up to more meteorological.
No, I mean air quality, it's just the air quality, the measuring of air quality levels in the air. But let's say in the air of the city without going to emission source. If you're going to have the average, let's put it like this, air quality, I need to have a station which is not close to, next to a traffic light. It's not very close to the parking area of an airport. It's not very close to the parking area of ships. So you need to know how the air pollution is distributed from Dassilio to Domenica to Rio, etc. So this is the ambient air quality. Okay, but if you want to measure the sources, then you have to go to the sources. This is something else. Okay, and then you have the methodology, of course, for all this. And there was another question. Yes, please.
We have all the air quality measurements, so we know what problems our city faces.
Ah, sorry. I was looking up back there.
Okay, I'm sorry.
But okay, let's just continue. Yeah.
Okay. So, is there any collaboration with the authorities so to take the proper strategies to face the problem?
There is always a collaboration with the authorities. This is happening a lot in most countries. Please.
Are there any pollutants that having a certain concentration of in the atmosphere is actually beneficial, or do they all, or is the ideal for all of them to be at zero?
No, it depends. Small concentration of pollutants are considered as beneficial. Let's say the first thing that comes to my mind is the small concentration of nitrogen dioxide. It's good in forestry. However, I don't know what is the critical value from benefit to risk. Yes, please.
In practice, how much time is required to set up such a system in a city?
Such a system in the city.
Is it a year? Is it 5 years?
You need at least a year of measurement to validate the models. So it would be more than a year because we need time to set up the stations, etc. You need also time to invest for the emission inventory. So maybe, I don't know. If you do it in parallel with different teams working, 2 years, I think it's feasible. Okay, you're welcome. Yes. Oh, yes.
So how much time do we need to create a robust emission inventory?
Let's say another year.
And how many sensors do we need to set a robust network in a mega city, not in a small city?
That it's
not considering the phrase "the more is better."
okay. You same thing like find in an intelligent way a number of stations.
The optimal network configuration
Yeah.
to start for our mega city.
Mm-hmm.
Not for a small city like Patras, or a mega city like Athens.
It depends on the type of information you're going to give. In all cases, you start with a basic number of stations by taking into account all these criteria. Then, for sure, if you analyze the result, you can understand that that there are places that you will need some stations more, okay? But then it depends on how detailed you're going to give the information. If you're going to give the information at neighborhood scale, so the number of stations is highly increased. If you're going to give a general information about the city of about, let's say, 5 by 5 kilometers, then of course you don't need such a huge number of stations. Nowadays at Patras we have around. George will present some results for 3 years of measurements with about 16 stations, and for sure this is not enough. At least it is only for particulate matter, for PM2.5, and this is not enough. We had to put more stations in the south area of Patras, in the suburban area in the south. We had to put more stations in the city center because there are a lot of sources there, and you will see more details in his presentation. Okay?
One more question?
One more question, yeah.
Okay. How difficult is to convince the authorities that we, together with a traffic sensor, we have to set a sensor that measures the air pollutants related to traffic, like NOxes. I think that it's not possible, but for an urban scale, I think that we need traffic sensors and air pollutant sensors. How difficult it is to convince them that we need more measurements about NOxes?
Yeah, actually, it's not difficult at all, but because you cannot persuade them, for sure. I mean, coming out from the, from the agencies that are responsible, the issue is that the official amount of stations for air pollution it's quite limited. I mean, for the full city of Patras, 2, and there are many towns out there or cities that don't have any measurement at all. I mean, if you talk about our greater area, there is. In the last 2 years, there is one station at the city of Agrinio. There is no station in Nafpaktos, in Negio, in Pyrgos, in every other place, in every other area by city. So I think that instead of trying to increase the number of stations, maybe in a city like here at Patras, first we have to put one station in another city, because the issue is that you may have some pollution there, but no one knows how much is this pollution.
I'm going to talk about our activities in the air quality framework regarding the EU directive. We have a quite complex system that involve several bodies as administrative bodies and technical scientific institutions. We are the National System for Environmental Protection, and we work together with several environmental protection territorial body that work in our 19 region plus 2 autonomous province. This regional administration are in charge for preliminary assessment, establishment of zone and agglomeration, regional monitoring, network planning and management, and so on, until the public information at regional level. Okay. The main ISPRA role is to support the Ministry of Environment in conformity evaluation of the regional delimitation into zone and agglomeration and the relative classification updates. We also cooperate with the environmental agency, European Environmental Agency, for filling the gaps regarding air quality assessment and reporting. We develop guidelines for air quality network development. And we evaluate the conformity to the European Community Directive of the Air Quality Regional Network project and their updates. And we carry out some assessment at the national level, particularly trend analysis. We also are the National Reference Air Quality Laboratory for Italy. So we do intercomparison with the regional agencies and QA, QC activities. And last but not least, we are the in charge for the national emission inventory, which is also a very important activities that we carry out. We are in the flow of reporting of official air quality information that come from the regional administration to us, that together with the Ministry of Environment make some checking, consolidation and aggregation, and then these data are transmitted to the European level. So going into the activities that can be interesting for these courses, Italy is divided as all the other member country into zone and agglomeration. We have a different zonization for the main pollutant, nitrogen dioxide, PM10, PM2.5, and ozone. This is related to the peculiarity of this kind of pollutant. And for the assessment of air quality is really important. A correct location of monitoring station. So the monitoring station are someone are located nearby the road, so our traffic station in a urban or suburban setting. Then we have background monitoring station that are more related to the assessment of exposure of population, urban, suburban, and then we have a rural station, that are far away from the main sources. And moreover, we have also industrial stations that are devoted to the assessment of quality around the main industrial setting. We have more than 600 measuring stations, and not all the pollutants are monitored in each station, but we have these figures of sampling point for each pollutant that are to be evaluated in the framework of the EU directive. So, which is the situation of air quality in Italy as for 2020 year? We have still a large number of exceedances for PM10, particularly for the daily limit, which is 5 microgram by cubic meter to not be exceeded more than 35 days per year. Regarding annual mean, we are quite well in terms of the limit values. However, we have to notice that in the large majority of monitoring stations, we have values higher than the short-term and long-term guidelines that have been set by the World Health Organization. So we have more than 80% of monitoring stations where we have values higher of this kind of guidelines that are setting to protect the population and to reduce. We have to tend to these values in order to reduce the number of people that can be premature death due to exposure to air pollutant. So we carried out trend analysis. We use the seasonally adjusted Mann-Kendall test and then tell-scene estimate of the slope, which is a way to assess the trend and to assess quantitatively the trend. So we can, using this kind of test, we can state if there is a trend and the statistical significance of the trend. So we have found during the last 10 years a statistically significant downward trend at the large majority of sites. This is an important thing because we are reducing the pollution through the year. With an average annual reduction of average annual reduction of 2.5% by year. However, we are still far from the objective, as you can see in this distance to target plot, where we have for each year the distribution of annual mean concentration of PM10, and you can see from the blue line that the trend is a decreasing trend as a measure of the concentration. However, we are still far from the World Health Organization air quality guidelines, which is this line. Okay, we are talking about nitrogen dioxide, which is another important pollutant, mostly related to traffic emission. We have a little number of exceedances of the annual mean limits, particularly in station nearby the major road. However, we are also in this case far away from the World Health Organization long-term exposure limits, which has been changed to 10 microgram by cubic meter in September 2021. Regarding the trend, we have also found a statistically significant downward trend for the large majority of monitoring station, as you can see from this graph and this map. And also in this case, we have a decreasing trend that can be observed also qualitatively by this plot, and the distance to target are as for PM10 very good regarding the limit value, but still largely higher. The values are still largely higher than the World Health Organization values. Regarding the ozone, we have practically in all the country exceedances of the long-term objective, which is the 120 microgram by cubic meter for the daily maxima of the running average, 8-hour running average. So the situation is also critical because we don't found any downward trend practically in all the country regarding this pollutant. Well, in Italy, we have a geographical exceedances distribution different in terms of zone where the exceedance happens. The exceedance happens mostly in the Po Valley and in other interland valley in the center of Italy and the south side of Italy. The Po Valley, as you may know, is a very large portion of Italy, over 40,000 square kilometers, with a large population, very important urban agglomeration like Milan, Turin, and many medium-sized urban agglomeration with little population but high population density, and last but not least, large arable land and permanent crops that lead to the large emission of ammonia and other pollutants, especially ammonia, which is an important precursor of PM, which is in the sense that particles can be formed into the atmosphere coming from this gas and ammonia and nitrogen oxide and sulfur oxide, leading to the formation of nitrogen ammonium nitrate, ammonium sulfate, that contribute to the concentration of PM. Moreover, we have the fact that the Alps at the north side and the Apennines at the south side of the Po Valley often limits the air currents between northern Italy and the rest of continental Europe. So, and moreover, we have feeble ventilation and wind calm condition the major part of the time, particularly in winter. So the mechanical turbulence generally low. This is a problem for the accumulation of pollutant. But another problem is that the mean seasonal planetary boundary layer height is very low. It's very low all over the Po Valley. This is an example for the southern side of the Po Valley. In this condition, low wind, planetary boundary layer 8, we have several days during winter that are favorable to accumulation of pollutant and formation of secondary particles. Not only the sulfate and nitrate of ammonium, but also organic secondary particles. And also that are also higher due to emission of due to the wood combustion, which is a way of residential heating, mostly used in all the northern side of the country, but also in other part of the country. This is, for instance, the number of days that are critical for PM10 or for PM exceedances that we calculate as days without rain, low precipitation daily, in which the daily ventilation index, which is calculated as the product of the average daily mixing age and the average daily wind intensity, less than 800 square meters by second. As you can see, we have during winter often more than 50, 60 number of days, which is half of the day, very, very critical for the formation of PM. Another example is from the central of Italy, which is the Sacco Valley, and near Frosinone, which is a relatively small town. We have, as a provincial, 600,000 people, population density not so high, emission medium, but we have, as you can see, during winter, very, very large concentration. This is January, this is December, compared with the other months of the year. For comparison, I'm going to show you the Rome agglomerate zone, which is instead very, very large, very high population density, higher emission, but due to the proximity to the sea, we have quite low level compared with the Sacco Valley in the hinterland. And also for comparison, here we are the coastal town zone, which comprise the Civitavecchia. It's an important cities for the port that and the activity near the port. But we have for the most favorable condition of meteorological conditions, so the data are much lower. We don't have much difference between winter time and summertime. Finally, just 2 words regarding the problem of dust intrusion that often happens in Italy. We have developed, following the guideline of the European Commission, a way to rapidly account for the contribution of Saharan dust outbreak episode to the PM10 concentration in all the stations of our country. We start from identifying the zero dust outbreak using the model developed by the Barcelona Supercomputing Center that are available online and give us the estimate 3-hour estimate daily at 10 by 10 kilometers that are available as a net CDF that can be downloaded. We identify these saran dust outbreaks, and then we select some regional background reference station in order to calculate the contribution with a statistical method that are found in literature. Then we link the African episode that we have found with the model to the air quality monitoring station. And the statistical method is applied automatically by a MATLAB script for each network station. These are the results for example. As you can see, from the north to the south, we have a larger number of days that are interested by dust intrusion. Not always this dust intrusion lead to an increase of PM10 concentration, but often the increase is very, very large, as you can see from this plot, where the contribution of the events by region are reported in this plot. As you can see, sometimes the contribution can be higher than 20, 30, 40 micrograms by cubic meter. And overall, this outbreak lead to also a contribution to the annual average, ranging between a few, some 0.2, 0.4 microgram by cubic meter in the north of the country, till 2, 3 microgram by cubic meter in the southern side. Okay, I think I've completed my time. So thank you very much for your attention, and I hope you have enjoyed this presentation.
Thank you, Giorgio, for this presentation. It came just after the talk about the EU regulations and how we can build a system for monitoring and management according to the EU standards. So it gives us a lot of information about the different pollutants, the importance of the Po Valley and the natural resources. Thank you so much. Unfortunately, we don't have time for questions because right now we're running out of time. However, we will have a chance to talk again close to the end when you present us the modeling results. So maybe we can summarize some of the questions and when going to the conclusions and the closing remarks. Thank you so much.
Okay, bye. See you later. Yeah.
Bye-bye.
I'm George Osmopoulos, and I am a PhD student at the... Okay. I am a PhD student at the Laboratory of Atmospheric Physics of the University of Patras. And today I'm going to talk to you about the capabilities of low-cost sensors to measure PM concentrations and to provide better insights on the urban air quality. More specifically, we'll discuss about a study case for the city of Patras, where a series of low-cost sensors were calibrated and then deployed across the city. So, conventionally, researchers use high-class instruments to measure PM concentrations. These certified instruments operate under specific protocols and provide high-quality data. But usually they are bulk heavy and very expensive equipment, so are spatially distributed within an area and are unable to capture the PM gradients within that area. So during the last year, there is a global turn towards low-cost monitoring techniques. PM low-cost sensors come in very small and compact size, They are very easy to use and they are inexpensive compared to the higher class instruments. Of course, they face several limitations. They are less precise than the research grade instruments. They must be calibrated before their use, and also their performance may be affected by the meteorological conditions, mainly the relative humidity. But still, they offer a very promising tool to create dense networks and gather a high quality of PM measurements. And so, for the study case of the city of Patras, our steps was first to select the optimal low-cost PM sensors, then to evaluate its precision and calibrate it with a reference instrument, and at last deploy the sensors across the city. We have selected the PMS 5003 sensors, which is one of the most widely used sensors. Very briefly about the operation of these sensors. You can see on the right figure that there is a fan that throws the ambient air through the holes. The particles into the sampling area scatter the light produced by a laser source, and the scattered light is then transformed to PM concentrations using an algorithm. So the first step of the analysis was to ensure that there are not faulty sensors and examine the intra-precision of the units. So several sensors were deployed, and the linear regression analysis was performed between their measurements. For example, you can see the results of the analysis for a pair of sensors. The results mainly the correlation of determination and the slope were close to unity, and suggest that there is a high reproducibility between the same model measurements. Next, we have the most crucial step of this study case, which is the calibration of the low-cost sensors. The most typical calibration technique is by collocating the low-cost sensors next to a reference instrument. In our case, you can see the collocation setup. In our case, the reference instrument was a Griman analyzer. So simultaneous measurements took place for more than a year, and the hourly concentration of the raw low-cost measurements were correlated with the Grim ones. In general, we can see that the low-cost sensor tends to overestimate the actual measurements, but there are also several observations, they are denoted with blue, that suggest that the low-cost sensor is unable to capture the real measurements and actually underestimates them. And the reason is why that happened. During the calibration procedure, several Sahara dust events took place in Patras. I think that you know that desert-originated particles are larger than the typical ones found in urban environments. So the low-cost sensor was actually unable to capture these coarse particles. So in order to conduct the calibration under the typical conditions of Patras, we excluded all these observations that correspond to days where the coarse particles were dominant from the analysis. Once again, a linear regression model was applied, and the results of this model suggest the calibration factor that we should apply on the low-cost sensors raw data. A calibration factor of 0.42 was calculated, and more information about this calibration technique you can find on our published paper on 2020. So, now that we have calibrated our sensors, we can move on and install them in several areas across the city of Patras. We have installed more than about 20 sensors, and you can see the location of some of them in this map. For this analysis, we have divided Patras in 7 different areas based on their topography and their locations. So, for example, you can see the background area denoted in red. The background area is located about 12 kilometers from the city center, and there are no intense PM sources during the whole year. You can see the city center area in blue, And in yellow, there is a cooking organic aerosol area, which is an area mainly affected by the cooking emissions. I will explain to you later about that. Have in mind that in Patras there are only 2 reference instruments, both of them located in the urban core, so their measurements are not representative for the whole area. At first, let's discuss about the spatial variability of the PM concentrations, about the PM2.5 concentrations. In general, there was a spatial heterogeneity across the city, with increased values from the background areas towards the urban areas. The lower concentrations were reported at the University of Patras and Platani stations located in the background area, while the highest was reported at the square of Triona Varchon, which is the cooking, the cooking area. Let's move on to the monthly variability. In general, for all the areas, there was, except of the background one, there was a seasonal variation with an increasing summer to winter trend. The background area shown in red shows that there isn't a significant seasonal variation, and the PM concentrations are rather stable during the year. On the other hand, the urban south area, the suburban south area, and the cooking area showed pronounced seasonal variation with increased values, especially during January, February, and December. And the question was why this happened. Some of you may already know that since the beginning of the financial crisis in Greece, there was a switch from the use of fuel oil to wood-burning fireplace that were used as the main domestic heating devices. So during the heating months, mainly January, February, and December, when the operation of the fireplace is increased, elevated values are reported to the aforementioned areas. We also examined the diurnal variation during the warm and the cold period. On the left figure, you can see the diurnal variation from April to October. From all areas except of the cooking one, the diurnal cycle was rather flat during the day, and 2 peaks were identified, one during the morning and a night one. These 2 peaks coincide with rush hours. And the most interesting fact here is the diurnal profile of the cooking area from 6 o'clock in the evening up to 12 o'clock at night. This station, as I mentioned before, is located at Triona Varchon Square. At this square, there are many restaurants and grills that operate during the whole year. So during that period, when the weather conditions favorable for people to go out, the operation of the restaurants, especially during the night time, provoke elevated values. And you can see that the maximum concentrations is reported at 10 o'clock, which coincides with the typical dinner time in Greece. On the right, we can see the same figure for the cold period from November to March, while during the day from 6 o'clock in the morning until 4 o'clock in the evening, the diurnal cycle was rather the same as in the warm one, with slightly elevated values, and the morning peak also coinciding with the rush hour. During the evening and night time, from 5 o'clock up to 1 or 2 o'clock at night, you can observe the highly elevated values. Once again, these values are mainly due to the operation of the fireplaces for domestic heating. Urban air quality is affected by both local and regional emissions. By regional, I mean the long-range transported particles. So it's crucial to find a way to estimate their contribution on the total emissions. So in this study case, we implemented the method developed by Diamantopoulou that suggests that the minimum of the diurnal profile of a pollutant is a good estimate of the regional emissions. So I'll give you an example. We calculated the diurnal profile for the station located at Daya during January of 2018. We found the minimum value, the 7.3 micrograms per square meter, and we assume that this value corresponds to the regional sources, regional emissions. So all values that are higher than this limit are due to the local emissions. This method was implemented for all the stations and on a monthly basis. The result of this analysis, here you can see the fraction of the estimated regional emissions to the total ones during the warm period in red, the cold period in blue, and the total period in black. In general, we can see that across the city, the regional emissions were dominant and accounted for more than, during the warm period, accounted for more than 50% of the total emissions. This behavior slightly changes during the cold period when decreased values are observed. For example, at the cooking area, the fraction was about 44%, and the background area where it was the highest was about 74%. And at last, during the total period, the regional source contribution remains dominant and was higher than 58% for all the examined areas. Finally, the monthly average local and regional contribution was estimated. In blue, you can see the regional emissions, while in red, the local ones. The regional emissions didn't show any seasonal variability. They were rather stable during the year with a mean value of approximately 6 micrograms per square meter. And in general, across the whole city, accounted for about 70% of the total emissions. On the other hand, the local emissions suggest seasonal variation, with lowest concentrations during the summertime and increased concentrations during the cold period. So, to conclude, we show the capabilities that offer the low-cost sensors for measuring PM measurements. They provide valuable information about the air quality in urban environments, and they can create dense networks with high spatial and temporal resolution that can stand as standalone networks or even supplement the existing ones. Thank you very much.
Thank you, George. Since you are here with physical participation, you will be open for questions during the coffee break that is coming.
Of course.
Just to save some time, please ask George all the questions about the area. But if you want, if you need to, let's say, to highlight something for a take-home message, we may say that, okay, 5 to 6 micrograms are regional sources, so you cannot do anything about it.
Yes.
I mean, it's just coming from out of the city. The most important sources, it's not the cars. Cars actually are less than 1 microgram per square meter. The most important pollution source for particulate matter, of course, is wood burning during the winter and cooking. You saw that what's happening at Triona Varchos area.
I think that the most of us, during the winter, we can smell the burning of wood, especially in the balconies if we want to put our clothes to dry them, etc. And of course, in Patras, during the Skynopempti, I don't know the English name, Fat Thursday, I think.
Crazy.
Once again, Thursday. We can see the effect of the cooking emissions.
Yeah, and finally, there is a gradient of pollution from north to south. So
From
this
yes.
area is considered quite clear. Also, the residences and the population is less, but also the meteorological conditions are different because of the wind. And if you go to the city center or in the south part of Patras, then the air pollution for PM again is increasing.
Yes, the background station and the suburban north station located here have totally different meteorological conditions, especially the wind favors the PM dispersion.
Great. Okay, thank you so much again.
Thank you.
It is okay, you are seeing it full screen, okay?
Yes, yes.
Okay, thank you. Good morning to all. My name is Georgios Grivas from the National Observatory of Athens, and I will discuss the implementation of sensor-based air quality monitoring networks in large cities, focused on the example of Athens. In general, air quality monitoring in European cities is conducted by state authorities that operate regulatory stations according to the provisions of the EU directives. There are examples of large metro areas in Europe where, through the cooperation of state, regional, and local authorities, the spatial characterization of air quality becomes very efficient. We can see here some examples, like in London, over 100 sites, Paris, Milan, and its metro area in Lombardy and Madrid. However, this is not the norm, as there are several major cities in Europe where networks are not that dense. Such an example is the greater area of Athens, the Greek capital. It is one of the 10 largest metro areas in Europe, with about 4 million inhabitants gathered in the central Athens basin and also at the adjacent Thriasian and Mesogia plains. The administrative fragmentation here is substantial, with as many as 8 regional units and 56 municipalities in the greater area of Athens, and these municipalities differ greatly between them in terms of population and population density. In this area, the Greek Ministry for the Environment is operating a regulatory network of 14 fixed stations. Now, those are not many, and what is worse is that they do not all record the full array of regulatory pollutants, as we can see here. In example, for PM2.5, which, as we all know, is one of the most important pollutants from a health standpoint, it is recorded only at 6 sites. While seeing the previous examples of other cities, one might wish for a denser network also in Athens. But the thing here is that the current requirements of the EU directive, this distribution conforms with the requirements, and this somewhat might impede the further expansion of the network. Now, the main air quality issues currently in European cities are well known, but in Athens, for several of them, there are specific aggravating factors. A key issue that we have here in Athens is residential wood burning during the winter. As research has shown, Athens is probably the most affected large city in Europe by residential wood burning, and during the winter nighttime episodes, concentrations of organic aerosol and black carbon become very, very high, and this carries important implications for population exposure. Moreover, there is the issue of photochemical pollution during the summer. It is intense in Athens due to the Mediterranean climate and also the basin topography. And as a result, ozone pollution, ozone breaches the EU target value on an annual basis regularly. Moreover, in Athens, there are about 3 million vehicles in circulation, and therefore there are several issues with exceedances of limit values for nitrogen dioxide and PM10, especially at traffic impacted sites. The vehicular fleet in Athens is very aged, especially for heavy-duty vehicles, where it is the most aged in Europe. And while in Europe there are currently talks about a ban of diesel cars, in Athens there was actually a ban up until 2011, but that was reverted. And since then, diesel passenger vehicles have flooded the market. And finally, the greater area of Athens has a large port, Piraeus. It is the largest passenger port in Europe. As a result, there are additional combustion emissions in coastal zones of the area of Athens. Moreover, due to the geographical location of Athens, its climate and its urban development, episodic air quality events have become very frequent, and this is concerning for short-term exposure of the population. Now, there has been a major wildfire event impacting the area of Athens every year since 2017, and the most recent one in late August that lasted about 10 days was rather severe, causing unprecedented air quality degradation in the area. This also made the international headlines, as we all know. There were also, during the last 5 years, 2 large industrial accidents within the greater area of Athens, and their plumes traversed the Athens basin, which also caused concern due to the potential of these emissions to carry very, very toxic, especially organic compounds. And lastly, as a city in Southern Europe, Athens is regularly, annually, every spring almost impacted by Saharan dust intrusions, and this causes rather elevated levels of PM10 and also PM2.5. Through the example of Athens, it can be possible to delineate some of the special needs for air quality monitoring in large cities. First, the populations are large, and this requires specially representative measurements in order to capture the within-city variability and therefore reduce the exposure misclassification error in the measurements provided by the network. And this can be very important also for health studies. Furthermore, in large cities such as Athens, that cover hundreds of square kilometers and have also a complex topographic relief, there can be large intra-urban variations also under the prevalence of different wind circulation systems. Moreover, different site types are required for monitoring, traffic sites, urban, suburban background, and that can be somewhat of a less concern in smaller cities, but not at large metro areas. As we saw with the example of Athens, there are frequently multiple stakeholders at the different levels, governmental, regional, and municipal, and each one has different air quality management needs, priorities, and require solutions for their own local issues. To satisfy all these needs with official regulatory stations would require a very large investment, a lot of money. Therefore, alternative solutions should become available. With their recent developments, sensor-based systems can comprise such solutions and help in the directions presented. It should be considered here that even though monitoring through sensor-based systems will never replace official air quality monitoring, they can still provide reliable information, especially in terms of temporal variability of concentrations, but only if they are properly calibrated. With this in mind, the National Observatory has designed and is pursuing through its participation in various research projects the integration of several monitoring platforms in order to maximize the availability of reliable data that represent spatial and temporal variations. For example, this is pursued within the SMERB's ERA-Planet project, it's a Horizon project, the Panacea National Research Infrastructure, and the Mission, that is a national cooperative project. The aim here is to explore how useful it is to integrate regulatory sites such as the one of the National Observatory in EO4GEO in Athens, with reduced cost sensor-based systems that provide calibrated data for various pollutants. Using IoT technologies, the Internet of Things, several products and services can be provided in order to inform the citizens and authorities and protect the population from unwarranted exposure. Regarding the sensor-based systems, we proceed with two main examples of the instruments that we are using in the National Observatory. First, there's the Perpular monitor. I guess this has been already presented by the University of Patras. So we'll quickly once more note that it is surprising how good it can capture the temporal variability of PM2.5 concentrations. It is also a very cheap device and easy to operate through Wi-Fi, so it can be deployed in dense networks, also with the active participation of citizens. A drawback here is that it cannot efficiently monitor dust particles. As we can see here, the comparison with a reference monitor. In the majority of cases, there is a very good agreement. However, during dust events, it tends to overestimate. Another system that we have extensively tested and deployed is the Hms monitor. This is a multi-pollutant monitor for ozone, nitrogen dioxide, and carbon monoxide, and other gases, also PM. And this can monitor gaseous pollutants reliably, which is important, given that such monitoring with electrochemical sensors is somewhat of a challenging target, given that there are several interferences from temperature or from cross-pollutant artifacts. However, we can see in the graphs that the measurements produce strong correlations with reference instruments for ozone, nitrogen dioxide, and even more for carbon monoxide. As we have said, it cannot be stressed enough how important it is to calibrate the sensor-based systems. In Athens, this procedure is carried out at the National Observatory of Athens super site that is located in EO4GEO, in central Athens, close to the Acropolis. And now this is a research site, an active site, and has advanced instrumentation for atmospheric composition, greenhouse gases, etc. However, it also carries the full array of instruments for regulatory pollutants, gases, and particles. The calibration procedure of sensors involves concurrent operation with these reference instruments, the statistical evaluation of the comparison, and the application of linear models for corrections. And also, we can say that it's very important to periodically recalibrate the sensors after they have been deployed in the field, as there can be various issues such as temporal drifts or aging of sensors, electrochemical sensors, season-specific artifacts. Therefore, it is important to recalibrate, and this can be done using, for example, identical pre-calibrated instruments or a mobile monitoring unit to calibrate on site. In the first step towards an integrated network, we have deployed 24 measurement locations of Perpular monitors, low-cost monitors in the Athens basin, and we are gathering their measurements every hour in an online platform. This is the platform, this is the site, the URL. We can see some of the visualization capabilities of the platform here, and also includes a color-coded air quality index in order to be more accessible for the citizens. This platform has been developed by the National Observatory for the National Research Infrastructure Panacea and gathers information from such monitors all over Greek cities from Panacea partners. The National Observatory has monitors in Athens and other Greek cities, and there's also a large contribution by the University of Patras with about 40 sensors in Patras and other cities in Greece. Now, while in the Panacea platform that we just saw, it is dedicated to PM2.5, we have also developed a network for multi-pollutant measurements using sensor-based systems in the Athens basin. Up to now, we have about 15 operating sites, and there are plans for expansion. Here, we are using the Hms system that we have presented earlier, but also some custom-made low-cost systems similar to the Hms that are developed by the University of West Attica. This is conducted this network in the framework of the emission project, and the emission consortium has also developed a smartphone app that provides personalized information based on the location of the user and also probably their demographic characteristics such as their age. The app can provide air quality indices from the nearest sensor and also advice regarding the current exposure risks. It also is possible to engage the citizens as through the app they can provide, for example, pictures or comments about their current perception of air quality. Now, regarding the applicability of all these measurements in real operational conditions, we present a characteristic example with the Panacea PM2.5 platform regarding the latest forest fires in Attica during August 2021. We can see in the pictures the evolution of the event and also the variation of the spatial variation of concentrations during this time. The fire started in the northern part of the Attica, the Athens basin, in August the 3rd, and by evening the plumes had already reached the nearest municipalities in northern Athens, with elevated concentrations starting to be recorded. And the next morning, the city woke up to find itself suffocated in smoke, with hourly concentrations, PM2.5, reaching 300 micrograms per cubic meter all over the place. Now, these fires lasted for about 10 days, and in this time, the platform was a rather useful tool for citizens, as we were receiving, the site, about 200,000 requests per day. And it was also used by the regional authority of Athens to guide their information actions. The necessity of a dense network during this time became apparent since the plumes were kind of moving around during this period, and conditions at the various sectors of the area were rapidly changing. Now, our goal here is to provide some kind of air quality monitoring at the municipality level. And I will close with some thoughts on how this network can be of use in the framework of a project like eShape. In brief, the eShape project aims to develop and support the exploitation of Earth observation services for decision makers in Europe. In the framework of eShape, the National Observatory coordinates a pilot that aims to blend EO platforms for air quality with socioeconomic and health data into an integrated risk assessment system in order to support decision-making by local stakeholders. The key tool used in the eShape project is a high-resolution city-scale atmospheric model. There's an upcoming presentation by Eleni Athanasopoulou, and there will be more details there. Now, with that in mind, we can see some possibilities that appear with the air quality monitoring in high resolution by sensor-based systems. For once, there is the chance for improved validation and assimilation of the atmospheric model, since the model has a very high granularity, 1 square kilometer or even less. It would benefit from the availability of rather spatially representative data. And also, as the eShape project aspires to provide the results at the LAU4 level, that is the municipality level in Athens, having one monitor at each municipality can permit the direct use of measurement data as inputs in the eShape platform. And that was all. Thank you for listening.
Thank you, George, for this presentation that gave us a nice overview about what has been deployed in Athens. Just give me a second to ask for questions, and I will I mean, pass it to you. Just give me a second.
Okay.
Okay, just I have answered the question, but it's about some detailed question about the calibration of the sensor. So I just answered that. If I want to make a final comment before the coffee break, is that is the next step. I mean, the next step after establishing such a dense network and have all the modeling tools, as you said, is try to estimate the exposure. This is much more important than just having the concentration levels, but try to find out how much people are exposed. And of course, the second step for the future is to how toxic are these, let's say, are these air pollutants, particulate matter. So this would be another issue. I mean, how it's not just the concentration, but the toxicity as well.
Yes, if I may comment on that, Andreas, regarding the exposure, it's very important, and within eShape, a methodology is developed regarding the calculation of this exposure using the tools, the modeling and tools in a dynamic manner, not statically, taking into account the activity patterns, commuting, etc. And also the toxicity is very, very important. However, we will have to see how it will be possible to characterize it using sensor technology in the future and what advancement will appear.
Great. So thank you again. We're going for a coffee break. We'll see you in about 22.
Are you hearing me okay? And you see my screen as well, yes?
Yes.
Okay. Hello, everyone. Thank you, Andreas and your team for organizing this interesting event. Together with my colleague, Andy, we'll have a presentation in the framework of air quality monitoring team. But before this, we shall introduce ourselves. We are working within Romanian Space Agency. ROSA, shortly, is a public institution under the authority of Ministry of Research. It coordinates national space research and application programs promoting space development. ROSA Romania is being full member of ESA since 2011, ROSA being appointed as a national representative. Since 2018, we are part of EO4GEO consortium, coordinating one of the work package tasks and being included and in several other work packages. Our presentation for today is on satellite data for air quality monitoring with a focus on anecdotal trends during pandemic times in Romania. The outline of the presentation is shared between the air pollution general facts, some ideas on satellites for air quality, Copernicus atmosphere monitoring service responsibility for the air quality monitoring, the NO2 data for Sentinel-5P during coronavirus outbreak in Romania, and finally the conclusions. So, according to World Health Organization, the air pollution is called the silent killer, as we'll all know that air quality directly affects the lives of most European citizens. Is a major environmental risk for health, and by reducing air pollution levels, countries could reduce health problems as heart disease, stroke, respiratory diseases. These pressing issues related to air quality is mentioned in the Agenda 2030 in the Sustainable Development Goals as well, on point 11. The United Nations Sustainable Development Goals raise the need to make cities and human settlements inclusive, safe, resilient, and sustainable. According to the European Environment Agency report, around 19% of city inhabitants in Europe are exposed to dangerous pollutants. No. I don't know what I've done. Just a moment. Okay. So, the IQ air rating, Swiss air quality technology company focused on developing air quality monitoring, make the World Capital City ranking, which reveals annual average of particulate matter concentration, where Bucharest is placed on 51 level from 92 world cities, having a moderate PM level. The ground-based data on national level are registered by the National Network for Air Quality, which make available daily measurements on particulate matter, ozone, nitrogen dioxide, sulfur dioxide, and the daily air quality index, being based on 24 hours average on hourly readings. Related to the different sources of pollution in the city we live, they were divided in several categories, I may say. The fixed source, represented by the industry, electrothermal power station, the mobile source, so very important to take into consideration, generated by traffic gases emissions, organic compounds, particulate matter containing metals, and surface sources represented by construction sites, residential heating, and other combustion sources. Lately, the mass media attention was focused on pollution due to illegal waste burning, which is a growing phenomena with the impact on human health and air quality in Bucharest and the surroundings of the capital. The illegal waste consists of electrical and electronic waste, car tires, recyclable waste. For the time being, the local authority are trying to permanently reduce this phenomena. As for the destructive environmental impact of oxide of nitrogen, I may say that the anode can be transported long distances on prevailing winds. Together with volatile organic compounds, cause damage to vegetation, crops, and lungs. It contributes to the acid rain with damages on forests, buildings, water sources, contributing as well to the global warming, keeping the earth warm. And it has an important impact on the visibility. And as I said in the introduction, the most important impact on health, which cause respiratory diseases. Related to our analysis today, I start by saying that satellite remote sensing is proving to be a helpful tool in the provision of air quality and climate data with high temporal and spatial resolution, which provide global coverage in a single image. Satellite remote sensing designed for trace tropospheric gases started in 1978 with Tom's instrument on Nimbus 7 satellite by NASA. A range of satellite sensors are used around the world for measuring air pollutants in the atmosphere, and we mention here OMI instrument on Aura, GOME on European remote sensing satellite. Among the latest is TROPOMI instrument for Sentinel-5P. The temporal resolution, as illustrated here, range from 9 days to 24 hours in the case of Sentinel-5P. The Copernicus Atmosphere Monitoring Service is one of the services offered by the Copernicus program, providing continuous data information on atmospheric composition. It is operated by the European Center for Medium Range Weather Forecasts. But in the same way, the European Organization for Exploitation of Meteorological Satellites supports this service by providing data and products from its own satellite systems. It's an operational information service for policymakers and citizens, offering near real-time services in the area of local air quality, health warning, aviation routing, maps and data for regional air quality forecasts. It uses observation from current satellites, including the Sentinel-5P. The dedicated atmosphere satellite missions, I already mentioned the operational one, Sentinel-5P, and we must include here the Sentinel-4 and 5, estimated to be launched in 2023. But there's the Copernicus dioxide monitoring mission as well included here, one of the Europe new high priority satellite, which will be the first to measure the carbon dioxide in the atmosphere. Sentinel-4 is designed to be a geostationary platform with hourly revisit time over Europe, with application mainly on air quality. while Sentinel-5 and Sentinel-5P, it's a low Earth orbit, daily revisit the time, global coverage, with application on climate, air quality, ozone, and surface ultraviolet radiation. Some general facts about the 5P is a precursor mission, focuses on global observation of the atmospheric for air quality and climate, bridging the gap between the instruments Chiamaki and OMI and the 5P, with improved sensitivity and smaller group sampling distance. The TROPOMI instrument is developed by the Netherlands Space Agency and ESA, with a mission lifetime of 7 years. It was launched in October 2017. As for the data products, it consists of aerosol absorption index, aerosol index related to dust outbreaks, volcanic ash, carbon monoxide, nitrogen dioxide, which we'll assess in our example for today, ozone, ozone layer, greenhouse gas, sulfur dioxide. It can be noticed in the present slide, the evolution, the air quality sensor monitoring as having a better spatial resolution from GOME2 until today, when we have in the era of Sentinel-5P. The Copernicus Atmosphere Monitoring Service is continually monitoring air quality in Europe and around the world using satellite and ground-based data. But today, in the context of coronavirus crisis, there is a permanent interest in changing air quality. That's why this service offers maps updated daily, which measure nitrogen dioxide, particulate matter with different concentration, and the ozone. Related to our study case for today, I must mention that coronavirus pandemic, what made us what are our intention to do this assessment within the coronavirus pandemic. Many countries impose national lockdown. Why? In order to control the infection rate, people mobility and economic activities being restricted. But the lockdown measures improved, we all know this, an air quality, and the measure reduction was observed in the nitrogen dioxide concentration. Such analyses were made by different international organizations as well as by Romanian Space Agency. Methodology and the results on this study case will be presented by my colleague Andy. Now I think I'll have to stop the share. And
I'll be quick because we don't have much time left. So in order to create a map and a study about the evolution of NO2 during the pandemic lockdown from 2020, we used the Google Earth Engine, which is a cloud-based service provided by Google. I will go straight to the results because we don't have much time left. Basically, we created a series of maps that span from the beginning of February until the end of March. And with these maps, we can clearly see that there is a strong reduction of in the NO2 values in Romania and near the border of Romania. So as a conclusion, the Copernicus Atmosphere Monitoring Service provides real-time, consistent and quality-controlled information related to air pollution and health everywhere in the world. Also, Sentinel-5P abilities enable us to detect atmospheric gases and air pollutions more accurately and higher temporal frequency than ever before. The cloud-based services such as Google Earth Engine offers us the ability to create very rapid and very precise computations on big satellite data sets such as the ones provided by Sentinel-5P. And also satellite data shown us a reduction of NO2 across the globe during the COVID-19 pandemic lockdown. So thank you for your attention. And if there are questions, let us know.
Thank you, Ioanna and Andy for the presentation. Unfortunately, we don't have so much time for questions. If I may have a short one, is there any metric, any quantitative number about how much NO2 has been reduced during the pandemic, based on your satellite information?
You want to know about the exact value?
Closely, yeah.
I don't have this information right now, but there was a strong decrease in the quantity. And the lockdown was like an engine for this that stopped basically the industry for emitting the NO2.
Great. Thank you again so much.
Thank you, Anthony, for the invitation. And we'll start immediately my presentation. We are discussing on in summary on two aspects. One is the satellite approach and the method to detect Saharan dust by using MSG Seriri. And the second part is related to the use that we can do of this kind of analysis in order to manage air quality in the city, in particular in the city where the traffic is particularly important in determining the PM10 pollution. As you know, we have different sources of PM10, which are anthropogenic and natural, and the impact of this of both PM10 pollution is regarding the human health. It's responsible of 6% of total mortality, and are well known the damage to cardiovascular and respiratory systems. And not the object of this presentation, you know, the important impact on climate, on the relative budget of energy budget of the Earth, and so on. Why we are interested to detect natural contribution to PM10 pollution? Because, you know, the European legislation obliges local authority when we have more than 35 sedans of this concentration, the threshold which is established in the 50 microgram for cubic meter, the authority have to take actions. So typically traffic restriction for several days until the situation is not changing. But the legislation, European legislation, allows to make exceptions when these accidents are due or related to natural sources. And natural sources are defined as you see in the bottom as sources which are not related to anthropic activity. And the most important, especially in the Mediterranean region, of this contribution are just the Saharan dust, which during the late, the start of the summer, in between May and June, interest quite all the South Mediterranean countries. Detecting sandstorm is not a quite a trivial issue, because they can be detected because like the clouds, they are very much reflecting in the visible. They can be considered colder. You can see in black this is a thermal infrared image, and the bright tone are related to the higher temperature, brightness temperature. So they can consider it also the lower temperature than the surface background. But this property has exactly the same of the meteorological clouds. So high reflectance, low temperature. So we need more to discriminate in between Saharan dust or dust storm in general and meteorological clouds. Most common index that has been used in the recent year is probably the split window of brightness temperature difference method, which really on the fact that looking to semi-transparent clouds, meteorological or dust clouds, the imaginary part of the index of refraction, which is responsible of the transmittance of the atmosphere to the radiation which leaving the Earth's surface arrive to the satellite sensor. This behavior is quite different. You see the black line, continuous line, is referred to the meteorological clouds. It's easy to see that in the band at around 10, 11 micron, the transmittance of the atmosphere is better than at 12 microns. So if you want, it's better to read this curve in terms of absorbance. The opposite happens for the volcanic ash and dust, for giant aerosols, which have are much more absorbing into the 10-11 microwave band than in the 12 one. So this means that when we observe the thermal infrared, the radiation crossing these two kind of clouds, we measure a major signal at 12 micron, then at 11 micron, when we have radiation leaving the Earth's surface that we assume at the same temperature is same brightness temperature, so it's crossing the dust layer compared with what happened with the cirrus cloud or a semi-transparent meteorological cloud. So at the end, the diagnostic element measuring the brightness temperature at 11 and 12 micron is that we expect that to have a negative difference, 11 minus 12, for in presence of dust layers, and the positive in case of clouds, meteorological cloud, and semi-transparent meteorological clouds. The threshold, the zero is the threshold established by Prata, Gu, and Lu. Is use a different threshold as minus 0.5, but generally speaking, these are fixed threshold method applied to the so-called split window brightness temperature difference. Who are the satellites which are able to make these measurements? We have several, in particular meteorological satellites are the most interesting because they have the best temporal resolution. And for the specific case, we don't need particularly high spatial resolution. Temporal resolution is much more important for several reasons. For instance, in our region, we are operating a polar satellite station. You can see the coverage is going to have just using one polar receiving station, and this is the case of our antenna for receiving geostationary satellites. So we can, this is important because you can understand that we can offer this service at a very large wide range of countries if you think about the market. What are the results? When we apply this kind of method, fixed threshold method, what we discovered that is not all things are going very well. We have a lot of false positive. In red, you see the pixel that in this image, which is the split window image difference between 11 and 12 micron bands, you see that no one of these red points is associated with the dust storms or the presence of dust. The same happened when we apply the method of Volu and or GU that you can see. You can see Prata, Lu, and the fixed threshold. You see for comparison in gray what is reported by OMI, which is in some way considered a reference data for the presence of areas. So you can see the major part of this red and blue pixel are false positive. And you see also the reason. You see the transit. You see that the distribution of this the split window signal is under this threshold in this area, but in this area we don't have signs. For the example, you see in this case that's the opposite. The Prata threshold is too low, and we have a missed detection. You see the sunstorm was present in this area, but the Prata threshold is too low, is not able to detect the signal, which is quite evident in this region. What is the problem? The problem is that when we define an anomaly in space-time, we have to exactly define what this means. Traditional fixed threshold method usually files for simple reason. If you have a signal that is as this behavior in time or spatial domain, usually people look for anomaly, looking for the maximum or for the minimum value in the time series. This is not exactly what we should do. And when we, for instance, discover that our threshold is too high, and so we lose a lot of events, we try to reduce the threshold, but in this way we include also maybe false alarms. And in the opposite, if you want a method which is much more reliable, we try to increase the threshold, but in this way we can also lose again some events. The way we are usually operating is not the same. When you have to identify an anomalous day regarding temperature, we never say if a temperature of 20 degrees or 30 degrees anomalous in say. All the time we refer this anomaly to the time of the year, to the place, because the same temperature can be anomalous in one place or in one time, but not in a different time. So in potential it will be quite normal to have a 30 degree in summer, but not in the winter or at Christmas. And for the same reason, a lower temperature can be anomalous or not, depending on the place and on the time of the situation. So we usually refer what we the signal that we measure to a reference, expected value, but also we consider also the normal variability of the signal. So if we have a change of temperature of 4 degrees tomorrow in my town, which is on the mountain, people will be scared. But if we have the same amount of change of temperature on the sea, in Metaponto Beach, which is not far from me, it will be a very big, huge changement compared with the normal variability of the temperature that we have on the sea compared with the land. So collecting this normal good sense information and applying them to the satellite data, what we developed and proposed is a method which is that we call robust satellite technique, which is usually considered. Please close the microphone. I have someone. So we prepare a data set which is built by satellite image collected at the same time of the day, in the same season, the same months of the year, to have the same emissivity related to vegetation. And we build this data set of as homogeneous as possible regarding the observational condition. We compute for each pixel the reference fields in terms of temporal average and standard deviation, so that this image contains all the information related to years of observation during the months of February, during the night, and so on, and define the anomalies not related to the measured value, but referring to the difference compared with the expected value weighted by the standard deviation computed for the same position in similar conditions. This quite the Ellis index that you see is defined with the double L as a local index that means local in the time and the place, because it's referred to specific observational condition at one place. With you applying this method, we published in quite all the field related to hazard, disaster, volcanoes, fires, floods, etc. In this case, in our case, the index is built by a preliminary analysis based on the visible and thermal infrared channels to identify clouds, and the last test is based on the BTD signature used at in our mode to discriminate in between clouds, meteorological clouds, and dust clouds. I have to find in San Nazaro et al. The description of this method. I rush toward the conclusion. Some example of application. This is a Saran dust event that we had in May 2008. It was quite important. We used the Severi on MSG with the split window. He has told the channel that we need. You can see the detection of dust storm over Europe. In gray, you have meteorological clouds. And the comparison with ground observation was quite interesting, because you see we compared our method with the one of Lu and Pratt, and you see that our map corresponds to the measurements made by the LiDAR system in Potenza, and also was confirmed by the OMI aerosol index. You see, we detect sandstorms that are not detected by other methods. We are also the comparison with the MODIS aerosol optical depth product was favorable. I skipped the other validation. This is also the validation with the Calypso LiDAR. When we compare this with the observational media at ground, you see the PM10 station in our region, from our regional agency, the regional representative of ISPRA, if you want. You can see the over threshold days, and you can see that it's possible to put in relation this over threshold measurement ground with the saran dust presence over the area in the same days. And this is something that can help the direction I mentioned before, but we can do also more. We can clean the time series of PM10 observational ground using saran dust detection by satellite to be the time series which are cleaned by the contribution of saran dust. This is important because at the end we can build a similar index based on ground-based measurements. We can have a reference field for these measurements at different time of the day. And so what we can do is obtain this kind of result. This is some series of PM10 measurements. It's quite easy to detect anomalies related to anthropic activity. But if we consider what we have done cleaning the time series, we can recognize anomalies in the signal. This is the Ellis index, which we are 2 sigma over the average, even in days, different days, not related to saran dust, because we can control. You see in blue, you see the day where we have saran dust contribution, but in this day, this is an anthropic anomaly that we can detect independently from the fact that it is up or down the limit of 50 microgram for cubic meter, just to detect something that is happening in the city that is anomalous compared with the history. That means also detect areas produced by people at work, for instance, or from other kinds of accident. I will summarize my conclusion. I think that I am out of the time. So we have just presented an algorithm to detect in a more reliable and way and with the higher sensitivity the presence of the storms. It's an algorithm which is exportable. We use on all the satellites which have the split window bands, and we can use this kind of product instead of the forecast maps usually used to make forecast on the presence of saran dust over an area. And it's very important that we can not just compare with PM10 time series, but also we apply the same method to ground measured time series to identify also anomalies, maybe under thresholds, but which are interesting in order to control the territory. Thank you for the attention.
Thank you, Valerio, for the presentation. Just give me a second to ask if there are any questions from the audience.
Let me. Please.
So, no questions from the audience. However, I would like to give us a short comment about the following. We show the importance of nature, of regional contribution in Italy as well in some maps in Greece, let's say in the Mediterranean. And we have discussed about it, the percentage of regional contribution to the measured levels. On the other hand, we have the regulation from the European Union that gives us a common threshold value for PM10 or PM2.5, which is, let's say, it's not fair in terms of anthropogenic activity, because it's true that in the south we have much more contribution from Sahara as well as other sources. So do you want to have a short comment on this, on possible ways to solve it?
Yeah, in fact, it's quite strange that we have a a threshold which is valid or not valid depending on the source. I think that the impact on the health is the same. It's not depending on the origin of this kind of aerosol. And also, I know that also this kind of limit is very much discussed. So we don't know enough about also the possible joint interaction of different pollutants. And this is a long history that regards all pollutants. But so I am not expert in this, not from the point of view of the health, not from the point of view of the chemistry of the interaction in the atmosphere and with the. And so I cannot say if this is right or not. What I can say that we are now, and also the presentation that we've seen before, in condition to put together this kind of information, so we can help a new legislation, because we have these instruments to monitor jointly several parameters. And the second aspect is that regard the way the agency are operating. So I've seen the nice presentation of Giorgio Cattani before. I think that it's not more enough that the Italian agency just control if some parameter is up or down a threshold. It's very important. I showed some example before that all anomalies are monitored, even if they are under thresholds, because they can be the signal of something which is happening in the environment that can be interesting to study. And I know that the personnel in the agency is very few, very operated by other kind of activity, but this is exactly the time when we speak about the transition, the green transition, so exactly the time to invest in this, to increase the number and the quality of people working on monitor environment and to control that what we are doing is actually compatible with the future, the life of future generation. This is my comment.
Research and okay, this is the table of the agenda of this presentation, an introduction on air quality operational service in Italy, one of the 8 national operational service in design phase in the Italian Space Economy Initiative. The engagement institutional part and the role of SNWF in operation or better in the development downstream services. And finally, I'll give the floor to Federico for a particular focus on case study on use Earth observation data to support estimation of wildfire atmospheric emission. As we've said before, the Italian legislation has delegated the Ambient Air Quality Directive competencies to the regions and the autonomous provinces, supported by the Environmental National Protection System. Here, the element necessary for the environmental agency to carry out the institutional task in the field of air quality, in particular, where remote sensing data concerning atmospheric pollutants are used in combination with in situ data to obtain information on the spatial structure of the pollution. Other useful remote sensing data are related to meteorology, land cover, and polluting sources. These data are used to improve the input and therefore the accuracy of the chemical transport models. All these elements are implemented in Italian Space Agency and ISPRA project, in particular air quality assessment and forecasting project, to design the National Air Quality Operational Service. This monitoring service has been identified by institutional users as useful to respond to the national and European obligation and monitoring national assets concerning air quality. This service is one of the 8 national operational services designed by the National Copernicus User Forum Consultation Board. The National Copernicus User Forum is composed by public, research, commercial, industry and enterprise user community representatives. These representatives are involved by an interaction methodology. For instance, for the air quality domain, each user identify for operational requirements the technical requirements specific. The first consultation and the first results have been published in the 2021, and now we could involve also the entrusted entities like SNWF that has been entrusted by the European Commission with the implementation of CAMS and climate service in the first Copernicus program and the first period of Copernicus program, and also in this second Copernicus program period 2021-2027. The Italian government, in fact, recognizes NWF like a unique enterprise in the field of atmospheric composition and climate, as well as on the management and the delivery of operational environmental services. So in the next January, the parties are going to sign a memorandum of understanding recognizing mutual benefit to cooperate in the implementation of the Copernicus Mirror program. Indeed, the role of expertise of SNWF is market uptake advisory for the set of the service identified by the national buyer group. Here, but before the presentation, highlight very well some few examples of the provided products for camps. It is important to underline that there is a value-added information based on satellite data and in situ data from the collaboration with the European Space Agency and the European Organization for the Exploitation of Meteorological Satellites. Here a screenshot stamp of the screen about the results and also the product with the analysis in the bottom, like fire activities analysis. In fact, concerning monitoring air quality and for this specific case study, estimation of wildfire atmospheric emission with Copernicus data, we needed to combine global observation and models, providing a daily biomass burning emission of various aerosol, greenhouse gas and chemical species based on fire radiative power, satellite observation, and in situ data. Here an example, a combination by the CAMS service chain. And now, if Federico is ready, I can stop my condensation.
Okay, can you see my screen and hear me?
Yes.
Okay, so here I will present an application and a specific focus on monitoring of natural hazards in the topic of impact on air quality based on Earth observation of stream surfaces. So how can we use Earth observation data and the derived product and information to generate estimates on greenhouse gases emissions that comes from wildfires. So first of all, we need to identify which are the areas characterized by wildfires and their characteristics in terms of the cover, which should be forest or natural crops, through a mapping that can be generated using Earth observation time series. Other information useful for the estimate of greenhouse gases emission is the fire radiative power that can be generated from the acquisition of thermal radiometries, like for instance in the Copernicus Sentinel-3 SL SDR sensor. Another information that is needed to characterize the area that's burned is the above ground biomass, which allows, together with the other information, to use coefficients and parameters for more accurate gas emission estimates like CO2, CH4, PM10, and so on. I will show now an example of how to generate burnt area mapping. This is a new methodology that we have developed in the framework of a project with the Italian Space Agency, and is focused on the identification of burnt areas for developed at local scale using different scenarios. That means identify burnt areas under different environmental conditions like climate, geomorphology, vegetation, and more specifically fire season, since the fires can also occur in drought years during the late fall season. And also land use, because we have the bad phenomena of stubble burning that is used for pastures and mostly during the summer period. The analysis of the burnt area has been done using Copernicus Sentinel-2 MSI data. And specifically here, I show how for 4 different study areas selected in this example, there is the possibility using different spectral band combination to see how the cover changes from the pre-fire condition, which have in green photosynthetic vegetation, which has high photosynthetic activity when it's bright green, and a bit lower when it's yellowish, and see how a different season, like in the left cases of Bussolena and Rivero, we have late fall fire, while in the right side of the screen of Rocca Gorga and Gravina in Puglia, we had a summer wildfire. The condition of the change is quite different. So the procedure that we have developed is based on the bitemporal analysis, so it's actually a change detection, and is based on different spectral indices. In this case, we have used 5 different indices. To use the bitemporal approach is just there is the need to compute the difference between a spectral index computed for the post-fire event minus the same spectral index computed for the pre-fire event. The methodology has been published in a research paper that you find in the slide, and actually makes use of an agreement index to combine the burnt area mapping that is derived, estimated from the different spectral indices. So here we can see how different indices has a different sensitivity to the changes from the fire, and the combination of the different maps can improve and reduce the omission, both omission and commission error, and improve the overall accuracy. It should be said that here this is a specific case. It's why I have selected for an example the dark, the black contour line polygon is actually the reference map that has been provided and used as for validation purpose. Actually, if we have a look at the top right image, that is a false color satellite image of the area after the fire, we can see how inside the area there are still areas that are photosynthetically active, and there are areas that are outside the polygon that are actually, that seems burnt. So here we should be aware of the data that we are using, and we see how high resolution satellite image can in some cases improve the information that can be generated from other services that are taking place. It should be also said that it might be that some areas, like forest areas, may have had an understory burning, so the canopy is still photosynthetically active while the grasslands in the understory has burned. So this has been a successful example of producing generated high accuracy burnt area mapping that can be used to improve the performance of greenhouse gases estimates, and hence the air quality monitoring from Earth observation and downstream services. Thank you.
Thank you both, Antonella and Federico, for the presentation. If I may ask something concerning the last slides from Federico, is there any how can I put this, operational platform that you can assess in near real time, or let's say after some days, the burnt areas, and or it's just something that comes after a longer term analysis?
Well, actually, there are two kinds of approaches when working and dealing with the burnt area mapping. One approach is to have near real-time data, and Copernicus put in place two different initiatives under the Copernicus Emergency Service. One is the rapid mapping activation. The rapid mapping activation is done with high or very high optical multispectral resolution data and are generated by operators. So there are some standard semi-automatic procedures that are verified. The other action that has been taken in place many years ago and is working quite well, and let's say that in the past few years with Sentinel-2, Copernicus Sentinel-2 satellite acquisition has improved also the spatial resolution and reduced the minimum mapping unit, is the EFIS. EFIS is the service provides for the monitoring of fires in Europe, and is under the Copernicus emergency and distributed and generated by JRC. This is the first approach, so near real-time information. The other approach is at the end of the year, when the European community wants to have information about emissions in atmosphere, then satellite data can be used for a reanalysis of all the fires in the year, and it can be done with maybe more complex procedures that require more time, but there is not the need to deliver a near real-time information, and that can be used to support the estimates of air quality parameters.
Yes, David, just a question, if possible.
Yes.
For Antonella, nice presentation. Thank you.
Thank you.
About what you're doing in ISPRA. Just a question, when you show the technical requirements for the air pollution and so on, I've seen that you ask 1/4 meters of resolution. Is too much or not?
Yes, but it is a need, not a need, but I think all representative wants the better results in the best way resolution, a spectral and the frequency, temporal frequency is very important to collect the needs and the requirement by all representatives, and the item of the Italian Space Economy Initiative is also to understand how to merge these huge needs and requirements and help deliver these requirements to research a innovative center like university, CNR, or so on, and develop the best product possible.
Much more as a provider need, data provider need than a user need, or not? Okay, thank you very much.
Thank you, Professor Tramosuoli.
As soon as possible. I have something to propose you.
And I would like also get for you, because you underline at the end of your presentation that we need to invest effort and budget in research, but also in a moment like this, where different representatives speak about this very important service, downstream service, not only research. Thanks.
Yes, great to think about. Yeah, thank you very much.
Good afternoon.
Λίγο πιο δυνατά αν γίνεται. Πίσω σε πιάνει, δεν σε θα πιάσει καταγραφή.
Should I take the mask off? No.
As a speaker, yes, you can take it off. As a speaker, you can take it off.
Good afternoon. I'm Yannis Kitsoukis. The talk is about forecasting particulate pollution in an urban area from Copernicus to sub-kilometer scale. This is a work that we've done together with my PhD student, Areti Papa. Let's start first with some basics. I will not say again the importance of air pollution and having accurate predictions of air pollution. I will just stick to the two the two fundamental different approaches to perform numerical modeling of air pollution, and modeling in general. The first one is the deterministic one. Well, it's called also full science approach. Here we integrate all the dynamics. We know the physics and the chemistry of the atmosphere. We put down the differential equations and we solve them numerically in a computer. This is the state of the art. Apart from the deterministic approach, there is also the data-driven approach. This is an approach, an input-output approach, where we have some data somewhere, and we believe that those data are influenced from some variables. We try to build a model that maps the input data to the output measurements. Just a very brief discussion about those two approaches. Maybe not, we are late. In the chemical weather models, the deterministic models, we integrate the equations in a grid. Okay, so what is the output from the model is the average concentration at each grid cell. And this grid cell has, can have a resolution either very coarse or very fine. Can be, for example, when you run a global model, this could be every grid cell can have a resolution of 30, 40, 50 kilometers. And if you'd like to do simulations for, let's say, the city of Patras, those grid cells should be very fine, so something like 1 by 1 kilometer. Okay, in the data-driven model, in general, as I said before, you should have measurements somewhere, and this approach gives you forecast in the place of the measurements, while the previous one gives you in that domain you make the simulation. So those are targeted only to the place where you have measurements. What's available and what's open now that we talk? Of course, you know the Copernicus service, and in particular the atmosphere monitoring service, which delivers operational forecasts for air pollutants in Europe at a resolution of 10 kilometers. Those forecasts come from a variety, several models, not only one, and they are for Europe at a resolution of 10 kilometers. So 10 kilometers, you can understand that for the city of Patras, it's just one value for the whole city of Patras, including also the suburbs. What's the concept behind this work? First of all, we would like to evaluate the CAMS particulate matter forecast issued at 10 kilometers at local scale, against a dense network of in situ measurements from calibrated low-cost sensor, as Yorgos, Vasilis, and Andreas presented at the beginning. Then we would like to investigate the potential of hybrid modeling approaches, combining deterministic models with statistical approaches to further improve the CAMS forecast and provide forecasts at a very fine spatio-temporal scale. During this validation, I will present statistics for different seasons, for different station types, for different forecast horizon and pollution levels. For the low-cost sensors, I think I should skip. It's something very new, and it's gaining a lot of. They're becoming more and more popular due to their affordable cost, provided that one can calibrate their measurements. As you have seen already in in the presentation from Yorgos, this is feasible, and so those sensors, the calibrated output from those sensors could be very, very precise. So, The two hybrid modeling approaches that I will present here are specific, namely the analog and ensemble approach and the long short-term memory neural network. In the first one, just one sentence for each. In the first approach, we seek analogs in a historic database of predictions and observations. In the second one, in the long short-term memory, we rely on past measurements of those variables. They operate they have different mathematics that they operate, and I will show what is their skill in this experiment. So, through a hybrid scheme, utilizing deterministic model from CAMS, so deterministic forecast from CAMS, plus data-driven models, as I mentioned here, ensemble, analog ensemble or LSTM networks, together with a dense monitoring network, we could obtain forecasts for PM2.5 and PM10 at fine scale. Consider that we start from CAMS forecast at 10 by 10 kilometers, and we would like here to show differences between stations that are the difference at stations that are inside a grid cell of 10 by 10 kilometers. Let's go to see the grid, the Copernicus grid for Patras and the location of the various stations. The black squares are the location of the grid cell of Copernicus. So you can see here centrally that there is only this grid point, which is representative for an area 10 by 10 kilometers around this grid cell, covers the whole city of Patras. So have one measure, one prediction from CAMS for the whole city of Patras. On the other hand, there are measurements at various locations from the purple air network, at various locations being either I can see here. This, for example, is Platani. This in the mountains. Here you can see Agios Vasilios, Castellokabos, University. Ψηλά Alonia in the center, and somewhere in the south there is also Koukouli in the industrial area. Okay, so I think you got the concept. Let's go and see how CAMS is compared against the measurements. First of all, to compare apples with apples. CAMS is a model which provides the average concentration in a grid cell 10 by 10 kilometers. We can compare this with the point measurement of the station. Somehow we should average first all the observations from Patras Air and compare this average concentration against CAMS. So, CAMS forecast is the one with the thick blue line, and the average concentration from Patras Air is the thick black line. Go back. What is obvious here is left is PM2.5, right is PM10. What is obvious here is that there is an underestimation of the concentrations during winter, an overestimation during spring, and things go nearly well for July, August, September, and October. What's behind? It's already said before that the inconsistency in winter is due to emissions not present in CAMS. And this, a very important contribution, comes from wood burning, which is not in CAMS forecast, in the emission inventory of the CAMS model. Okay, so for winter, we know the reason, and of course you can see, and you can see the very high spread in winter between stations. Here, in the bottom line, you can see the rural stations, here the University or Platani, where the ones with very high concentrations are in the center or in the industrial the industrial area. Now, compared to spring, the consistency here in spring, well, here it's not CAMS is right here, and purple air, those low-cost sensors are not able to capture the Sahara dust events, which occurred in April of 2019. So this inconsistency is due to this. Go further, and so I would like to show now time series, not averaged over the year in a monthly scale, but in hourly scale for 2 weeks of January, where very high concentrations were measured. This is the station in Psylla Alonia, central station. With the red you can see Patras air, so there is diurnal variability, which is not captured in the blue line in CAMS. Again, remember that CAMS operates in a 10 by 10 kilometer scale, while Patras air, the measurement in Psylla Alonia is a measurement around the station of Psylla Alonia. So consider this difference as well. And now I will show what can the statistical methods I said before can achieve. In the same plot now you can see with the black line the analog ensemble method, and with the green line the LSTM method. Both of them go very close to the Patras air measurements. Remember that we started from what is the input in those models, the CAMS forecast at 10 by 10 kilometers, plus the measurements at local scale. And just by bringing this information in the right way together, you can have very precise forecasts at local scale. It's evident that analog ensemble captures better the peaks. You see the black line is closer to the red one than the green one. This is one case for Psylla Alonia in January where very high concentration occurred. And this is a typical the time series for April, so I would like also to show the case where the CAMS prediction was the right one. You see, even if in the models we give something a wrong measurement, because at the time of between 12 and 13 of April, we know that the measurements of Patras air were wrong. Even in this case, they were able, their predictions are very robust, and they were able, even under such conditions, to improve what is measured from the Patras air. We proceed more. We saw here the evolution of forecast skill. You know that as we leave a model the simulation of a model proceeds in time, the forecast error increases. CAMS provides 4-day ahead forecast, so up to 96 hours ahead. What you can see here with the blue line is how the forecast error increases as time passes. It starts from here, it's normalized error, starts from 0.8 and gradually increases. There is an increasing trend in all the plots. The peak, of course, is around at the local time at 18 in the afternoon, when the peak concentration are observed. But you can see for the other two methods, for analog ensemble and LSTM, that the degradation of the forecast scale is much smaller. And especially for analog ensemble, it's almost constant in time. The red, as you can see, the trend for the red curve is almost parallel to the y-axis. So here also in numbers, there is a very, very small increase in forecast error in analog ensemble. Just comparing all the three methods together through this, which is called the soccer diagram. Left is CAMS, in the center it's analog ensemble, right is LSTM. The x-axis is the normalized mean bias error, while the vertical axis is the normalized root mean square error. So ideally, of course, ideally we would like to have something as close as possible to the 0, point. What is evident is that, let's compare, I don't say anything about CAMS, because now we see what's happening at the station scale, but I compare analog ensemble with LSTM. It's visible. Okay. At which stations we observe highest errors? Highest errors, this is in the vertical axis, at the station of Koukouli, industrial station, at the station of Psylla Alonia, central station, urban traffic station, and what's the else? Hagia Sophia, again, station in the city center. And the smaller error is seen in suburban stations in the University of Patras and in Platani. You see that in analog ensemble the spread is smaller, while LSTM has a very high spread between stations. Let's move further to extremes. Here we show how the models behave with respect to very high values. So we would like to see when for PM 2.5 we have measurements over 20 micrograms per cubic meter. And for PM10, when Patras Air recorded concentrations over 40 micrograms per hour. The first index, which is called probability of detections, shows how many from the cases that were observed are actually correctly modeled. For CAMS, it's only 6% of those stations. For analog ensemble, it's 52%, and for LSTM, it's 20%. This remains the same also for PM10. You can see that analog ensemble does much better compared to LSTM with respect to extreme values. I will not go to the other two. The other two, it's the second column is the false alarm rate, which means that analog ensemble will say, for example, or any model will say that we'll have an exceedance tomorrow, and exceedance will not be observed. What does this say here? That for analog ensemble, I have 52% probability that when there is existence, it is also predicted, but also 46% probability that it predicts existence and is not observed. Of course, you can see that this, even under this situation, this is even better compared to CAMS, and similarly the same with LSTM. The gross index, which to account not only the hits, what is accurately predicted, but also the false alarms and the misses, is this index, the CSI, which you can see how much better is for analog ensemble compared to the other two methods, again, especially with LSTM. And I would like now, as Δύο. Okay. The last you remember at the beginning, I wanted to show you if those methods can predict the spatio-temporal pattern of air pollution. Left is CAMS. For CAMS, there is only one point for all Patras. So you can see the bullets are the colors correspond to the measurements for Patras air. There is one prediction for CAMS which says something between 10 and 15 microgram per cubic meters, while you can see that the measurements show that in Koukouli I have values around 40, and this is Psila, Alonia, and here is the center. And in the north, the concentrations are very closer to the to the average, to the CAMS forecast, but in the south, close to the city center, they are totally wrong. And here also you can see the forecast maps from analog ensemble at the center and LSTM at the right. They are able, especially analog ensemble, to correctly represent this north-south gradient of air pollution. Okay, so all those results are in those conclusions, and just to sum up with I will not say again that there are different season, different station types, etc. That combination of deterministic models, for example, CAMS, data-driven models like analog ensemble and LSTM, air pollution monitoring at a dense network obtained from the low-cost sensors. All those together adds value to the system, providing accurate PM predictions at fine scale. And of course, the prediction is always very important when can contribute significantly to public health awareness. How much I have? Some. Okay. Thank you very much.
Temporally resolved data. We need long-lasting time series for long-term exposure, and we want also to take the seasonal and daily variability, other than to find the difference in terms of concentration in a more or large spatial domain, can be urban setting or also neighborhood, or national or continental scale. So which is the general statistical modeling approach? We want to find a statistically significant relationships between the target variables, which is the concentration that we want to assess the health effect, and several spatial and temporal, or both, predictor or explanatory variables. They can be various kinds. Based on these relationships we want to estimate on the whole interest domain the target variable. So we need to know the predictor values and the model coefficient values. But most important, we have to have reliable concentration data at a large number of monitoring stations. And if you want to capture the spatial variability within the study domain, it's really important where these monitoring stations are located. Moreover, we need explanatory variables dataset for each sampling point, and most important, all the cell of the main cell grid for all the time that we want to estimate. This is an example approach using a simple multilinear regression, which is the basis for land use regression models at urban scale. Here we are going to estimate the particle number concentration, which is a proxy for ultrafine particles. Ultrafine particles are those particles with aerodynamic diameter less than 0.1 micrometer, so very, very little particles that are, in terms of number concentration, the large majority of particles in the air. While the mass concentration is mostly dominated by the so-called accumulation mode, which is particles from 0.1 micrometer to 1 or 2 micrometer. So it's a really different kind of measurement between particle number and mass concentration. Mass concentration is measured at fixed monitoring sizes as PM10 or PM2.5. Particle number concentration is only little monitored in sparse point. So we need to, and most important, we don't have at all reliable emission inventory. So chemical transport model or even Lagrangian model cannot be applied since we don't have reliable emission inventory for that. So we need to carry out specific purposed monitoring campaign, and then we have to apply statistical modeling. In this case, we do that for Rome, measuring ultrafine particles in 28 point, and then we apply the land use regression model methodology that was already standardized in a previous European study. Okay, this is the result. As you can see, the model predictor are, as we can expect, traffic density on major road, but also population density and urban green density. And another important factor are the building street configuration. All these predictors enter the models and explain a portion of the spatial variability. As you can see, this is only a spatial modeling. Also, we can obtain a very high resolution spatial estimate. However, we don't have temporal resolution. The lack of fine spatial and temporal resolution and pollution assessment is the main drawback of most epidemiological investigation. We cannot rely only in monitoring network. Certainly, we could assess the spatio-temporal variability using deterministic model, chemical transport models, and so on. But statistical models are generally easier to implement. We can include complex correlation structure via easy to specific random effect at a low computational cost, which is also important. It needs only medium-sized computing resource and provide higher resolution spatial prediction generally when we go to a domain such as a whole nation, for instance, as we do for Italy. Why it allows to capture the small-scale spatial variability around main source, which is one of the drawbacks of chemical transport models that are more prone to estimate well an average of concentration in the cell domain, instead to capture the variability, the small-scale variability around the main source, such as a road and traffic sites. Moreover, this kind of modeling, statistical modeling, provides sufficient temporal resolution, typically daily, which is largely sufficient for epidemiological studies. So let's go to some example. I go very rapidly through that. This is a national scale statistical spatiotemporal modeling using the linear mixed model frequentist approach. As you can see, we have a good picture of the country variability, and this model is also both spatial and temporal at daily resolution. In this case, explanatory variables used also some satellite-derived observation, which parameter, which is the aerosol optical depth, using the MAYAC algorithm, which allows to improve the spatial resolution of the aerosol optical depth provided by satellite at 1 square kilometer resolution. All the variables were easily available and can be used easily. Also, most important, are available for all the country in order to model the concentration. The fitting or the model estimation show a very good model, very good performance in terms the root mean square error predicted. As you can see in this graph, we have the correlation between predicted and observed concentration, and also the square error, the R square is quite good. By ranging between 0.78, 0.68, 68.75. Okay, but the spatial and temporal root mean square error AR square were good, but possible application in this case, since we have modeled several years, are also trend analysis or other than application into epidemiological studies. But there are some some drawbacks in linear mixed model. So, which is the fact that the spatial dependencies is expressed to discrete random effect that are related to geographic defined areas, in this case, the region. So the result, we have found some spatial artifact in the prediction maps. Moreover, this kind of approach, statistical approach, do not incorporate in the final product the whole uncertainty associated with the unknown data parameter and structure. So we move to a Bayesian approach, the Bayesian hierarchical models using the INLA SBD approach. We have no time to go deeper in these topics. You can see that into the publication that I have cited. Sorry. Okay, in the previous slides, we selected the 11 predictors, which are meteorological parameters, temporal, so they are temporal variables, also planetary boundary layer at different times, and aerosol optical depth, dust intrusion occurrences, and other spatial predictor, which are altitude, linear distance to nearest highway, imperviousness. Based on that, we have this is the results. As you can see, we have both daily variability and tempo and spatial very nice resolution. We fit this model based on log PM10 mass concentration instead of simple PM mass concentration. As you can see, we fit a model for each month, and then we have the results in terms of root mean square error, which are very good, and correlation and also bias very low. The application, as you can see, can be various. We can obtain a very accurate average concentration, so population exposure average at municipality level, we have enhanced spatial coverage and reliability. We can also use this model to calculate PM10 exceedances probabilities by day, as you can see, for example, for today in January and in July. But we can try to use this kind of approach also for intervention analysis, which is assessing and quantifying space and time the effectiveness of unadopted strategies. We do that, for instance, for the Italian 2020 COVID-19 lockdown, which is can be considered as a not desired intervention analysis, by using the as a predictor variables the ratios between nitrogen dioxide concentration in 2019 and in 2020. By making this, we take into account the effect of weather and other confounding factors, as well as the spatial temporal correlation existing in the data. So we can evaluate the effect of the lockdown continuously in space. Also in this case, each month was modeled separately, and we fit the spatial temporal model for the difference for the reason using the same approach, Bayesian approach we see before. Okay, this is the results. It's a collection of weekly continuous map describing the spatial pattern of the relative change in nitrogen dioxide concentration in Italy for the period of the lockdown. And so we have both spatial variability of the relative change and also temporal variability, since we have done this for each week of the month of March and April. All these maps are available at this site, which is the Pool Virus project. So thank you very much for your attention. I don't know if I am right on time. Anyway, thank you again. I can't hear you.
Sorry, we have to make some arrangements in the sound here in order to avoid the echo. So this is the reason that I was a little bit late to answer you. Thank you again for the presentation about modeling. I think that with this presentation, we have a nice overview of all the activities of ISPRA. And
good afternoon. I am Eleni Athanasopoulou. I am a postdoctoral researcher at the National Observatory of Athens, and my expertise is on atmospheric numerical modeling. Today, I will discuss about two projects that NOAA participates and are relevant to urban air pollution issues. I will focus on these aspects of the projects. The one is SMERBS, and I will give focus on two solutions that are developed in this, that are relevant to air pollution and modeling activities. And the other, and then there is eShape. Both projects are funded by the Horizon 2020 Research and Innovation Program. So eShape is a running project actually now, while SMERBS has just ended. And they are, let's say, connected, at least with respect to NOAA. We were based on SMERBS knowledge, experience, and outcomes. to lead one of the pilots of eShape that is related to air pollution and health risks at the urban level. So just a few things to say about why we focus in cities. Air pollution is one of the largest environmental threats and health threats globally. And air quality standards are exceeded in many urban areas around Europe and globally. So this is because people are there concatenated, and also the large emitters are in cities such as traffic or industrial sites and wastes. Which makes the concentration gradients high, and so we need air pollution modeling in finer scales to represent this variability and go further into health studies. And this, of course, needs support from emission inventories that are again of finer scales. With this in, let's say, as a motivation, back in 2016, we built the SMERS proposal that became a project running for 4 years up to now. So 19 partners gathered together with expertise in Earth observation. Actually, we have collaborated with Ioanna Vlad from ROSA and her team in this project, as well as with ISPRA, but with a group on urban growth issues. As you see here, a lot of Earth observation platforms were combined and focused on the urban domain, taking into account the stakeholders and the users' needs from different type, such as citizen, authorities, industry, people from the industrial sector, and so on. And we finally developed a lot of solutions that target on air pollution issues, disaster issues, and city growth issues. These solutions are gathered in a portfolio that I will show you here online. It's a dynamic portfolio in the sense that we can sort solutions by themes and by the platforms utilized. We can go through them, you can go through them, they are all in the official web, SMERS website. I will focus, as I said, today on solutions relative to air quality and in solutions relative utilizing models and Copernicus outputs. These solutions are implemented in several cities. We can see online the network of cities. As you can see here, Patras is also in the network because we have collaborated with Andreas and the team. And you can see, for example, here one of the web of the pages that shows the implementation with basic information on the city, which are the pressures that are addressed and why. And how? I guess earlier on in the morning, the network of sensors there was described. I wasn't able to watch. So as I said, I will focus on two solutions that are of European coverage, not in the sense of of European coverage, but still focusing on cities, but not just one or two. They can be applied in any European city. First, the urban tool is a numerical tool that we developed at NOAA in collaboration with the Helmholtz Institute to produce, to downscale regional emission inventories to high resolution emission inventories. So here you see the emission inventory, that the basis is the emission inventory provided by CAMS. Here with a paradigm over Athens, you can see the original spatial resolution of the emissions. And what we have done is to use high resolution and publicly available and of high quality data relevant to land use and other information, for example, core land cover, global human settlement layer, so that we arrive at emissions in 1 by 1 kilometer. By using the OpenStreetMap data, these emissions, the road emissions are attributed to the road network. While by using information from the EPRTR database, the industrial emissions are appointed to the points of these sites. So this tool is described better in a recently published paper in the Atmosphere Journal, where you can find more information on the tool, as well as the website. You can download the software that is behind this tool, and it can be used by anyone to produce a high resolution emission inventory over any area of Europe. As I said, or I don't remember, anyway, we have applied this tool over Athens and Hamburg in the frame of SMERPS, also for the Ioannina city, and last for Helsinki in the frame of the shape project that I mentioned in the beginning, and I will show later on. The other solution that is of European coverage, although targeted in cities, is the SMERPS SDG indicator 11.6.2 Earth observation platform. Earlier, the UN SDG framework was mentioned by Joanna, I think, that let's say supports the welfare of the planet and of humans. The SDG 11 goal is relevant to cities, and the indicator 11.6.2 is relevant to air pollution. So the PM2.5 mean annual mass concentrations weighted per population are calculated, and this is the SDG 11.6.2. In SMERPS, we have realized that focusing over cities is of importance, because then you have a chance to make targeted decisions on how to address, let's say, the indicator. So we decided to calculate an SDG 11.6.2 equivalent, in the sense that we have selected, we have defined the urban areas either as urban centers or as functional urban areas, which are definitions provided for the definition of city. And then we have calculated this SDG for each urban center or functional urban area of the whole Europe. So this is done for several years, and there is also a way to select each city of we want to explore, and plot also the trend, and compare among cities, compare among the definition of the city, compare among years. We have used this platform to raise awareness to citizens. We have given it to students, and dissertations have been made based on this platform. You can also visit it and explore it by yourself. Here is the URL. So, as I said, ESAPE is a European project that supports EO4GEO and supports Europe in exploiting and demonstrating EO capabilities in a European level and in a global level. So the main concept of ESAPE was that a partnership experts on Earth observation come together, exploit their experience and solutions, co-design, create added value products which will be co-designed with users so that these solutions are uptaken by users and are useful to them. So I think more than 50 pilots are executed at the moment, and we as a group, the Atmospheric Chemistry and Physics group of NOAA, coordinate one of them, which is the pilot 2.3 Earth observation-based pollution health risks profiling in the urban environment. You can see also the partnership below. So the point was to provide air pollution data and combine them with health aspects and socioeconomic features in the global level, but also in the urban level, and cooperate with stakeholders from the health sector or other sectors that are interested in air pollution data, to produce trends and also real-time information, to raise awareness on air quality implications on public health. And the way to do it is to, you can see here, we combine geographical and temporal scales of different EO tools, of in situ measurements, of modeling data, of satellite measurements of air pollution, and create synergies among different EO data and health data, and to have some pilot cities to showcase the output. And actually the outcome is a platform which is now under development that will be a global service in the sense that it will cover globally a lot of cities with relevant information, as well as the cities that you see here in the vertical, that have different, let's say, targets and interests. The platform is not, is, as I said, under development, but I can show you how it stands at the moment. So here we see, as I said, it will be populated with more dots. We can see, for example, that when we focus over Munich, actually, we can see annual values of a health risk index by by municipalities around the Munich area. We can see the mean and the maximum values of this risk index. This will be the content of the teaser platform, but each city will develop their individual platform with more information than the one that is shown here. Then if we see what is over Finland, there are maps of NO2 from Sentinel-5P that are downscaled down to 1 by 1 kilometer. And some information on the point sources of the area, as well as of the air quality station information on the area, are also there, and will be, as I said, more as the platform evolves. For Athens, as you saw, the content is under development, but I can say a few things. What we are currently building is a year of high resolution air quality modeling outputs that, of course, will be complemented with the measurements Yorgos Grivas showed in the morning to you. The model is a high-resolution atmospheric Eulerian model that simulates the physical and chemical processes in the atmosphere. And we are planning to go further towards population exposure to this pollution, and a combined outputs relevant to health. I think that was all I had to say in terms of time as well. Thank you very much for your attention and the invitation, of course.
I don't know how possible it would be to have a discussion open to the public, because this is a hybrid physical and virtual participation was a challenge throughout the day. Although we also have to leave at the auditorium at 3 o'clock, so if you don't mind, we will stop the webinar, the presentation from distance, and we will make the wrap up here with physical participation. But if there are any comments from anyone, we'll be more than happy to get it. As I said to Giorgio, I think to everyone in the chat before, that this was a very rich in terms of content workshop. Probably we should do it for 2 days instead of 7 hours. But however, yeah, it was so much information. I hope that the students had the possibility to go a step closer to reality, get out of the auditorium and face the real problem and the solutions, of course. So if there is any comment, please, you're welcome.
I agree, Andreas, was a good initiative, good quality. I think that there is room to organize a stable meeting, a meeting for this group on this topic, not just because we had this initiative today, but because the quantity of available data and also the progress in this direction are very big, and also there is a huge perspective for the future. I don't know if you are thinking to organize some specific workshop on this years, or in the GU or some international conference. It could be the occasion to have a permanent update on what is happening. In any case, thanks for the invitation. It was a very nice initiative. So I need to meet you again in the future. So try to organize something.
And I guess it would be interesting also to bring together people devoted to health assessment with us, which are most exposure assessors. So it will be interesting, really interesting. Also, the presentation of Valerio and other people. We have some to talk about regarding the dust assessment. So I was impressed also by the LNE presentation, since this project seems to be really in perspective important, because I think it covers most of our attempt to assess spatial and temporal variability over pollution in a organized way, and also comparable, because it is also important to apply the same solution to different parts of the continent, in this case in Europe. So really interesting.
So Joe, you are proposing some interdisciplinary meeting. So having both parts should be very interesting. I agree.
Great. So yeah, it's good that there's a field for further collaboration among the presenters as well. I hope that in the continuation, if any and how, of EO4GEO project, and the need to repeat such training activities, we'll have the chance to do it again and go deeper and further.